We have many talks today, so we better start on time. And what time is it?
We still have 2 minutes. But...
Okay.
I'm sorry, I just stood up to be ready. But
so it's we didn't receive the talks, didn't get the talks from Emmanuel Oliveira and Chandan Mondal. So if you are here, just send it by email to the or upload in the Indico page, or give it to me in a pen drive during the break or now. And so with that, I think you can say some introductory words for us. It's going to be a 40 minutes talk about something which is a very hot topic now. I'll give you 10 minutes more, right? So you have 40 minutes, but
yeah,
after 30 years.
I'll try to be on time. Right? Okay, and leave some time for questions. I can make the story longer, but I tried explicitly not to push it.
O pessoal está ouvindo? Let's check if the people from Zoom, are you with us? Can you hear us? Young Lee, for example?
Yes. Yes, I can hear you clearly. Thank you.
Very good. So I think we can start.
All right.
So,
all right. Good morning, everybody. First, I would like to thank the organizers for the invitation. I've been in Brazil twice, but the first time in Rio, so I'm actually enjoying it. I'm going to focus my talk today on new results that we published recently, around March. And from my perspective, it's an interesting subject, and we are somehow at the dawn of this subject, which is talking about the accessing the gluonic structure of the nucleon at its kind of simplest level. And of course, as time goes by, people are trying to really dig in and try to get all the structure of the proton and nuclei, but the gluonic structure. All right, so the talk will be based on this paper. However, there are some extra results that I'm going to show that are preliminary because things are moving slowly and interesting things are happening. So now, when you talk about gravitational form factors, as I will mention in a minute, you realize that the mass of the nucleon, which was a question posed yesterday by Dr. Elke Aschenauer, in terms of one of the questions the National Academy puts in terms of motivation for the EIC, you wonder, how are you going to tackle this question about the origin of mass? So there were questions about origin of spin. We have an idea, we have studied the spin a lot, however, we still have a lot to learn. On the other hand, mass is something where you wonder, what can you do? Because we have measured it precisely. We know the mass of the proton. And through a fantastic tour de force, you know that in 2008, the spectrum of baryons was calculated with lattice QCD, and the nucleon is sitting here, but of course we have the other hadrons. And in this case, with few input, which is the fixing the pion mass, the kaon, and the cascade up here, they were able really to reproduce what we know. And this, I think it's a major result. And then they went on to even look at differences between protons and neutrons. So if you, at this time, if you talk then to people and you say, okay, what else do you want to learn about this? You're done. Lattice QCD works and everything is great. The problem here, of course, is kind of a black box, maybe not for the lattice people, but for everybody else. At the same time, you want to go beyond this so that you can, for example, try to understand the distribution of the mass inside the system you are studying, like the proton in this case. On top of it, you might want to know what is the part coming from the gluons and the part coming from the quarks. So these type of detailed questions as you try to push your knowledge becomes very important. And that is really why it's at some point important to, at least in simple terms, have more and more information so that you understand the role of quarks and the role of gluons in providing the mass of the nucleon. Now, as we know all, the Higgs made a lot of noise, and we all understood through all the explanations that were out there that this provides masses for leptons and quarks. But in looking at the mass of the proton, which is 1 GeV compared to the mass of the constituents, of course, 0 for the gluons, and the quarks are few MeVs as far as the light quarks that form the proton, there was a kind of a puzzle in terms of how does the mass of the proton comes about. In fact, if you look at the public lectures, one of them was that of Susskind at Stanford, trying to explain why the Higgs is about something, not something else. He mentions in his public lectures that there are examples in nature where the Higgs mechanism has nothing to do in providing the mass, and he gave the example of a cavity with infinite thin walls where you put a lot of energy through electromagnetic fields, and that thing has energy, and E equals mc squared, therefore you have a mass. In nature, actually, there are two examples. The proton is one of them, and you could say all the hadrons. And then the black holes also, you convert and you discuss things in terms of energy. So the idea is that this is a special place where we can study a system, and it's actually quite exciting. There has been a series of workshops since 2012. I will mention in the end this experiment at JLab that was called SOLID. And in the early time, we tried to motivate as I will show, the access to a term that's important. And it's only important from an experimentalist point of view if you can measure it. So, you can have a lot of theoretical discussions, but in the end, you'd like to do some physics by being able to measure something. And as you could see, there is a kind of timeline, and the last workshop happened at the INT in 2022, where people were discussing different mass decomposition in terms of the constituents, and also trying to understand the subtleties. In the meantime, the LHCb discovered its pentaquarks, and that gave really a motivation to many people through suggestions of many theorists that you should try to produce the J psi on the proton by photoproduction and show that maybe you can see these special states that were seen in the LHCb. These are the charmed pentaquark states. Well, with that, it was around 2015 where the LHCb saw its pentaquarks. 2016, we then proposed an experiment in Hall C that I'm going to present. 2019, another detector at JLab have seen the first J psis. and didn't really see much of or at least didn't see a big signal on the pentaquark, then the experiment in hole C, which I will describe quickly, happened in 2021. And we started to analyze it, and the results came out recently. The key is that that experiment went in fast. It was an experiment that was just for 7 days. So it turns out 7 days at 50% efficiency means that you run in real days something like 15 days. And we didn't expect really the results that we found. Of course, we were after the pentaquark, and we saw something else in terms of interpretation. All right, let me now just say a few words about the mass of the proton. We heard a lot about the energy momentum tensor yesterday, and it's key at the heart of the discussions about the mass. So if you go to textbooks, they will tell you that basically if you take the energy momentum tensor and you take the trace of the energy momentum tensor, you have these two, I would call them two terms if you put all the quarks together, but here I separated the heavy quarks from the light quarks. The G's are the gluonic fields. And if you take the trace of that, so this is a T alpha alpha of the energy momentum tensor, you have this thing that's called the QCD trace anomaly. So if you look at this part on the right, because you could rewrite the heavy quarks in terms of gluonic fields, you see that this expression up here became same expression, except that this beta function has a tilde on it, okay? So you have a term that's related to the quarks, or quark masses, plus this anomalous term here, the gamma ML. This is something that has some log term in it, and you have the trace anomaly. Now, if you take the chiral limit and say that the constituents, which are the quarks, have zero mass inside the nucleon, is the nucleon has a mass, right? To do that, there is a relation that tells you that if you take the matrix element of this T alpha alpha, which is the trace of the energy momentum tensor, you get P mu, so you get the invariant, which is the mass square here, okay? Now, if you take the chiral limit, you put this term to 0, you end up with this term, which is non-zero. For the nucleon, however, it's funny that it's also 0 for the pion. So the pion is different from the nucleon. So in some sense, if you take the mass of quarks in the pion to 0, you get 0. The anomaly contributes, the sum of it contributes to 0. However, for the nucleon, we know this is around 800 MeV. It's almost there, okay, for the mass. So you could say that, okay, all of this is interesting. So that tells you a little bit the mechanism. But to me, the real question is, can we measure this matrix element directly? And that's the puzzle. That's still not obvious. However, as I discussed the gravitational form factors, you will see that they are so important that there is perhaps a path to get this matrix element through measurements at the EIC, for example. So all of this is in the works. Just to be complete, that term on the right actually has been studied maybe for 30 years, which is the pi nucleon sigma term. So this matrix element here, people have done measurements, theoretical studies, and they pulled out these numbers. So for the up and d quark piece, 59 MeV. For the strange part, there has been progress, and now you have a number with a smaller uncertainty. And all of this is documented here in these papers in terms of how much the part that is quark related is taking, okay? So you're taking about 100 MeV, and then your proton is 928 MeV. So that's why typically, if you hear people saying, okay, the quark take 1%, that's not this term. They are just talking about the mass of quark 5 MeV and 6 MeV. But really, the right way to think about it is you have 10% basically taken by this quark term that is the pi nucleon sigma term. And then the rest is really gluonic fields. And that's the part of the anomaly that gives you your 800 or 90% of the mass of the nucleon. All right, now I like this picture. Elke in her talk had a different version that's actually, I would call it more detailed and accurate. This is to try to really get the message. I don't expect to, go through things. But the one thing I wanted to point out that I will bring back later is the fact that first, you need a frame here, and we heard about Light-Cone yesterday and Light-Cone formulation. The best way right now, of course, to discuss, for example, elastic scattering of the proton, elastic electron scattering of the proton and charge distributions that you extract through Fourier transforms and so on, and GPDs and TMDs is a unified framework. And that's really the idea. So this is actually progress from the theoretical point of view, that you could observe everything within the same frame consistently. And why am I saying this? Remember, you measure a charge distribution. We have measured it for a long time. I mean, since Hofstadter. And the point is that people now are still trying to measure the slope at 0 to get the radius. Right? And we know experimentally you never get to 0 and you have to discuss and debate extrapolations. But what's interesting is that if you go to the light front description, what happens is that you not only worry about q square equals 0, you actually can use data to q square all the way to 1 in a consistent way. And you are looking at a transverse charge and you don't worry about relativity and boosts and mingling of all kinds of interactions. So now, why do I have this? So let me just go back one step. Oops. Oh, it's this one. Yes. So this is an electromagnetic form factor that I'm showing here, right? But in the hierarchy, of course, if you had the GPD, for example, you could go down to the form factor. So there is consistency that you need to make sure exists by the time you get all these GPDs for quarks and for gluons. The key I'm trying to say is that the gravitational form factors are a very elegant way to study something that's beyond the charge distribution of the proton. So what you are doing by studying the gravitational form factors, you are looking into the mechanical properties of the system. And in those mechanical properties, you do, they are momentum transfer dependent, and therefore you can actually look at distributions of mass density, pressure density, shear forces density. And I listed here 4 of them. Usually you could see only 3 if you mix quarks and gluons and add them together, you have only 3 gravitational form factors. But if you separate quarks and gluons, you end up with 4 of them called A, B, C, and C bar. And I will say more in a minute. All right, so let's talk about gravitational form factor and what are they? Well, they were shown yesterday. I think, sorry about this. All right. Yes, the first thing I wanted to do is to give you a comparison between elastic scattering, where you are trying to measure a charge. How do you do elastic scattering? You don't break the proton, and it's interpreted usually with 1 photon exchange, right? And with this, you measure the charge form factor. Now, imagine you wanted to, but the charge is carried by the quarks. Now imagine you wanted to reach the gluons inside the proton, but they have no charge. They have a color charge. Then you think, well, let's try to do a color scattering. Well, too bad. If you try to do a color scattering, you are violating here some conservation of color. And with that, you can't do it. And the question is then what to do to access the gluon density. Well, what you could do is elastic scattering of a particle like the J psi, which is CC bar. And the J psi doesn't exchange quarks, right? The proton has a very small probability of intrinsic charge, so I'm neglecting it even if it's there, okay? 1%, yes, somebody said it yesterday. Well, in that case, most of the exchange happening here is two gluons, it's through gluons, okay? I'm sorry, I shouldn't say two gluons, I said through gluons, which means that through this, you are probing the gluonic content of the proton. Now, the question is, how do you interpret that? The problem, I don't have a beam of J size. And you might ask me, oh, why you didn't choose the phi? We are going to stick with heavy quarkonia because, again, for the theoretical interpretation, it's a much cleaner when you're trying to expand and then keep a certain number of terms. So the best thing after having a beam of J psi, I think, is to do photoproduction and electroproduction of these heavy quarkonia by producing J psi or upsilon for that matter. When you look at this diagram a little bit in more details, you can see that the exchange, for example, the photon converts in a QQ bar, which then picks up the quantum numbers of the J psi. However, you can see here that I have ... which means you can have an infinite number of gluons there. I don't know how many, but you will see that it's a lump at this stage. But important, you do not break the proton, and the decay is easy to detect here because the J psi decays 6% of the time in a pair of E plus E minus, or 6% of the time roughly in a pair of mu plus mu minus. All right, now, the key here is that I would like to access these gravitational form factors, and I would like to access the gluonic part of these gravitational form factors, and that's why I was discussing the experiment with which I think I can access them. So what am I trying to access? I'm trying to access the matrix element of this energy momentum tensor. And please forgive me, the quarks are important, of course, but I'm not going to discuss them here except to mention them as I go through to compare relatively the contributions. So here they are. I wrote them, and there are 4 of them. And the one that we have a very hard time measuring is this one, C bar. So for now, we don't know much about this C bar. However, one thing you need to know is that C bar, the gluons and C bar of the quarks, they cancel each other. They have opposite sign, and if you add them, you get 0. So that's why I told you if you add quarks and gluon, this term disappears. But look at them. This A of Q square, if you take the 0 value of the momentum transfer, you find something that is common in deep inelastic scattering. So we heard about the PDFs, and this is the fraction of the momentum carried by the gluon inside the nucleon. This we have measured, and we know this number, right? Also, if you manage to get B precisely and A precisely, here is the total angular momentum, okay? And we know that it's 1/2, so if you take it at 0, that's what you're supposed to find. And now is this C form factor, which sometimes is called D because of the drug term, because DVCS and all these GPDs. So these form factors was discussed a lot in the framework of trying to do fits for the GPDs and identifying all the terms that were important. But here, in terms of gravitational form factors, we call it C. It's just, there is a relation with this factor 4. But it's related to pressure and shear forces, okay, in the nucleon. So this was not that much known. Yesterday, I saw Jim Very showing some results from JLab, but those were really hard extraction on the quark side for these. So it's not an easy business. You have to deal with the GPDs and do some integration, blah, blah, blah. What I'm showing you here is the gluons and the gluons with the shortcut. What I mean by shortcut, the GPDs are ultimately what we want to get with the EIC, the gluon GPDs. And we better in the end find consistency. Okay, but here I am trying to access them in a with some caveats, as I will mention, but you will see what happens. All right. Once you have these gravitational form factors, you could ask a question about, for example, how does the mass distribution radius, right? So the matter radius in the proton, because it's energy, so it's mass, how that is compared to the charge. Is it smaller? Is it of the same size? Or is it larger? And you will see there's some surprising, interesting results. So this is the type of question you can ask if you can manage to get these gravitational form factors. So I will talk about the experiments at JLab. There are 4 holes at JLab, and 3 holes have taken data and should have J size in their data tape. However, I will discuss the first, at least the results from BlueX, the newer ones, and then I will discuss this experiment in hole C, which is not a large solid angle detector. Class 12 also has measured J psi, but they are having issues because, again, it needs luminosity and it needs good acceptance. And this is a cartoon. It's a project in the works for a long time. I don't know whether I should call it project, but for now, it hasn't received CD0 in the language of DOE, and therefore we are trying to push because it will take large intensity and large luminosity. This is the hole C measurement that I mentioned. So this is one of the holes at JLab. And what did we do? So what is the experiment? The experiment is you come with the electron beam of JLab, you convert it into a Bremsstrahlung photon beam through a radiator here of roughly 10%. Then you go through a hydrogen target, you produce the J side that decays right away, and you detect the electron in this super HMS spectrometer, and you detect the positron on this HMS, sorry, high momentum spectrometer. So that's a good question. The outgoing proton in this experiment, we don't detect. And I'll tell you, because we assume it's an elastic reaction, we can reconstruct the photon energy. It's very hard to detect the proton with the luminosity that we have here. And however, if you look at hole D, the other hole, which is a large acceptance, they do detect the proton. So your question becomes then how do you know that it's an exclusive process? Well, because we are at threshold and because the spectrometers have very small solid angle, we actually have very little, if known, and we confirmed it in the experiment by seeing events outside the kinematics where they should be, which tells you that you are reconstructing things the wrong way. Okay. Oops, did I? So, bottom line, it's this diagram. We do not detect this proton. However, through the decay of this, we know everything about the J psi. And the proton initially was at rest. And therefore, assuming that the proton hasn't broken, we can reconstruct the energy of this gamma beam. What you see down here is the energy of the photon and T minus T min. So T is the momentum transfer, it's the P prime minus P. And these colors and these boxes are the bins that we chose in that phase space. So we are very close to threshold. The threshold is at 8.2 GeV in photon energy. T min, there is a minimum T, the J psi is 3 GeV, the nucleon is 1 GeV, so you are not going to produce it at very small T when your photon energy is close to threshold. It's about 2 GeV, so we are starting from 0 just because we are subtracting T min. But as E gamma goes higher, we actually are able to, of course, lower the T min. All right, I told you about this, so I won't repeat myself. but it tells you here how, what type of detectors, and we are quite sure and we understand quite well these spectrometers. Why this is important is because you are going after an absolute cross-section. So from an experimental point of view, not dealing with a large acceptance detector is a little easier as you study these spectrometer acceptances quite well. Here are the results. It's not maybe sharp and the lines are a little bit fainted. And what am I presenting here? I'm presenting a color code for the bins corresponds to the color code on these graphs here. The energy is plotted on the top. So this is the lowest energy that we measured. And you have a T distribution in this axis. So the horizontal axis is T. And you could see that it's T. It's not T minus T min, which means the lower the photon energy, the closer to threshold, the larger the T is where you start measuring things. And then we compare this to different calculations. And you see they are all recent. I mean, 21, 22, and so on. But what we did with our data is we didn't send the data to the theorist and told them to put their calculations. We actually reproduced their paper because they gave enough information to actually really check what their curves are. And then we plotted them because they all have some parameter that they fix, and they were fixed on GlueX experiment, which published before us. But it published with less statistics, but they had an idea already. What you can notice here is that at large energies where GlueX is, all models are kind of doing okay. But then as you walk down, you see the dispersion. I'm not claiming that our data tells us which model is better than the other. I'm just showing that, look, it's kind of nice to not let the theorists have their hands. I'm sorry for that. On the data ahead of time, so that it's kind of a prediction. And I will make some comments on that too. So I'm showing also here GlueX data. So they took their data, which are the red points, and they compared them to our data, which are these black squared. And they are published. So these data here are the same as I showed a minute ago. You could see this is a slide from Lubomir Pencher from Hall D. And you could see that the uncertainties, scale uncertainties on GlueX are 20%, while the whole C is 4%. As I told you, spectrometers can give you a more precise cross-section measurement. So this is important. Moreover, if you look carefully at the bin sizes, they have 3 big bins. We have 10 at least bins that we dealt with. And the point is that our bin size is consistently 150 MeV in photon energy, so that we can see trends as a function of square root of S or E gamma. While with 3 bins, of course, your average is so large because their bin size is about a GeV. Okay? All right. So what did we do after that? We basically took advantage of all these bins and all these T distributions to make a fit of these models that exist. And we took two models, and we did the fits ourselves in the sense that it was important for us to see whether we can extract these gravitational form factors, and you cannot extract them in vacuum, you extract them with a model, okay? So we chose 2 models, the GPD model, that's described here. So you see it's 2 gluon exchange. I'm not saying 2 gluon exchange is the right thing, but then you could see how bad it is or good. But what we did is a 2-dimensional fit. And I wrote here some of the expressions. You could look at the paper, is listed up there. We checked also their formulas in such a way that we understand what we were doing. The other interesting model was this holographic QCD model. So this is a model that's, per definition, working in a non-perturbative regime, because this threshold region is non-perturbative, and that's why I don't know how many gluons are being exchanged. And you could see here, for example, that there is the A form factor, and then there is the D, which is 4C form factors. And this is split in two pieces typically in their calculation. They say that what we are probing is components of the energy momentum tensor. One of them is spin 2 and the other is spin 0. Spin 2 correspond to a graviton type exchange, and spin 0 is a scalar field. I don't know what type of scalar field. That's always very difficult. But this is really fantastic, because what this is saying is that you are probing specific kind of mixture of gluons configurations that are in the proton. And you try to get that. What we notice is that this model seemed to track the energy dependence better than the other models. This model cannot fix all its parameters. It can calculate everything except the normalization, just so that you know. So there is no model here that can do everything with no parameters fixed. The type of form factors we took are dipole type form factors shape. And that's motivated because of the lattice calculations. All right. Here, I'm really sorry, the colors somehow, yes. So what you are seeing here is the A form factor and the D form factor. So we took the holographic and the GPD. The holographic is this, let's see, it's this brown color. So the A is known quite well, and the GPD is the green. As you can see, the green is offset, but the brown, we go all the way to 4 GeV squared. And then you might ask me, what is the blue? The blue is the lattice. The lattice was a prediction. I have to give it to them because they, did the calculation before they saw any of the data. Okay, and we were shocked to see that we are doing so well. We are doing so well with the lattice on the A form factor, and we are doing so well with the lattice on the D form factor. And this is the first time you see D is negative. This is the first time we can claim, okay, we extracted from our data through a fit this D form factor. This approach is the holographic approach, okay? And as I say, there is a normalization. However, the others are coming 3-parameter fits from our data directly. What's the conclusion? The conclusion is the following, is that if you write now, you have the form factors. That's what you measure, assuming the caveats, but you say, I pulled the form factor. As an experimentalist, I'm done. I mean, then you can argue all kinds of things, Fourier transforms, so on. If you have been doing charge form factors, right? Many people want to give you then the Fourier transform, the density, and then argue about all kinds of things. I can do the same here. So we said, okay, let's get the radius. You can define the mass radius of the gluons and the scalar radius. So when I say mass radius here, it's dominated by the slope of this A form factors. And then, as you can see, there are combinations of A and C. So what's the picture that emerges from this? If you look at the holographic numbers, so these are the parameters that we extracted from our data because we took dipole form fits, and the A0 form factor, as I told you, you get it from PDFs. It's very well known. We took CT18 as the type of global fit. And you could see how well the lattice and the holographic extraction are doing. It's almost the same. So the mass is 0.7. We know that the charge radius is about 0.84, right? And that tells me that the mass is smaller than the charge radius, where the quark likes to live. Now, one thing that's very interesting is the scalar radius. The scalar radius, by the way, is bigger than the charge radius. So remember those pictures? You have now a mass of the gluons or energy of the gluons that's at the center, but doesn't mean that there isn't some energy going out beyond the charge radius, but it's scalar in nature, okay? So that's really the picture, and this is kind of exciting, but you have to take all the caveats for now, because we need to move forward, try to understand things. The GPD, they updated their paper. They found some issues with this green curve. So now once we took, again, the new posted paper and we did the fits, they are closer for the A form factors. The yellowish is the holographic. But notice that we need C0 for radii, and you see that the new green is going high here, and that changes things. We get the curve, the pressure curves again. So if you have the D form factor, you can get the pressure distribution, you can get the shear distribution, and you can see that lattice and holographic are doing okay. When you are looking at the GPD approach, it's a little bit off, and I think they know that they have some work to do because of the expansion, and I don't need to at this stage get too much into the details. I generated this recently because I wanted to express things in light front. What I didn't tell you is everything you saw before is in the bright frame, and then you can argue extrapolation, so on. I wanted to put it, and this following Cédric Lorcet paper, I checked his formulas, and this is what comes out, but I wanted to put the gluons and the uncertainty coming from our experiments. The blue and the black is the sum, the blue is the quark, but I don't take the quark seriously. This was like a theory guess of whatever numbers were there, okay? The blue has to come from DVCS, and it will take some time, right? Because you have to have the Fourier transforms and so on. But the advantage of this, first, remember, large B perp. So this is B perp, which means this is the transverse dimension as you are going out from the center. The precision typically, remember, is that large T means small b. Well, large T, we don't have enough statistics, which means more data is very important. The point I'm trying to make here is that because we are on the light front formulation, this actually can be linked to the bright frame, and it's all discussed in this paper. But what I like about this is it really uses the large T data quite well, and it's quite important so that you don't have an issue with the recoils and so on. All right, now that I have 1 minute, I'm going to just quickly tell you that there is a spectrometer called SOLID. It's large solid angle for large intensity. And we will be able to do J-psi production in it at Jefferson Lab with 12 GeV at threshold. These are the projections that we can do. These are the type of T distributions that we can do in electroproduction and photoproduction. Photoproduction here and electroproduction here. And with that, it means we can fill more statistics, and it's important. The punchline really is at the EIC, because whatever I told you, it's very exciting, but we heard yesterday about universality. Whatever you pull as gluonic information, you better know that it's going to be the same whether you use this probe or the upsilon. And we can do the upsilon at the EIC. It's harder to do the J-psi at threshold. However, we are looking into it because if you go to large Q square at threshold with the J-psi at the EIC, it may be possible. And what that does for you is to go after this anomaly, after this C-bar form factor. So there are discussions that about C-bar form factor. So here is what you can do with the upsilon at the EIC. So what you see here is the total photoabsorption, photo production cross-section. More important, each of these points that you see here, they are either, as you can see here, at 10 inverse femtobarn or 100 inverse femtobarn. They are plotted with data that exist from LHCb and so on, which are at very high Q square. There is nothing, it's a desert in the region of threshold. And what we want at threshold is to have distributions. These are the T distributions that we could extract when we combine them, extract these form factors. So with that, I conclude by saying that to really have an insight into the origin of mass, we need to understand or try to measure directly the trace anomaly. Lattice QCD is doing a great job. However, I feel that this is actually a beginning, and this is a shortcut before we have all the GPDs of gluons from all the labs in the world, okay? Because then you can say, I can integrate and get the gravitational form factor from up, down. But here I'm going through threshold and try to pull them right away. And my hope is that using the upsilon will allow us also to check and understand better what we are extracting and check universality and check the trace anomaly. So thank you very much.
Thank you for this excellent talk. We have time for some questions.
Congratulations for a very nice talk and very interesting results. About the holographic QCD, there are some models in the market, and you mentioned 3 parameters that you can use. Can you talk something about that?
Yes. So in what I showed, there were 2 types of calculations, something they call the down-up and the top-down type holographic model. So Hatta had one calculation there where he says it's top-down, and that was an early calculation. And Zahed and Mamo had this bottom-up. Now, what I didn't show are the details where actually for this holographic, they can calculate even the functional behavior in terms of T has nothing to, you don't need to put any shape or form factor. For example, I said, oh, I take a dipole, and that's how I can do my fits. But they had a complete function. And we programmed that when we were trying to compare directly. But to extract a result, you could see that that function was not so different from a good dipole form factor. You could take a tripole if you want. What they cannot do, so they can get the functional form. And they have one parameter, this kappa, they fix with rigid trajectories, and then that's it. What they cannot do is tell me what is the absolute value of the total cross-section. And that, of course, I can't either. It's fixed on whatever the data are. So if you just calculate, they have put it from glue X. So I didn't need to change it. I kept that, but then the dependence in T, it was 2-dimensional because we had enough bins in E gamma and T distribution to actually fix 3 parameters. A of 0 was fixed from PDFs. So I didn't want to even, we didn't want to look at the lattice, because when you compare to lattice, you might say, oh yeah, we can take the same number. No, we took the experimental from the, the best fits within the uncertainties. They are very well known once it's integrated. And then you have the C form factor at 0 that you need to get out. It's a negative number, which came out from the fit. You need to get out the lambda, so the scale for the C form factor in a dipole fit or a tripole if you want, and also the A form factor scale. And those are about 1 GeV, which tells you the scale of the stuff that's being exchanged.
Thank you, Zin, for this very stimulating talk. Could you show again the transparency with the radius?
Yes.
The 2 radius. I'm puzzled and I want to ask with you.
Yes.
Yes.
Oops.
Yes, that's
Sorry.
right.
Here.
So the matter radius,
Yes.
from the contribution of the gluons, I think naively we can understand why it's smaller, because you need to go, when you start to put other more gluons, they are a kind of massive inside, we know from lattice, inside the nucleus. And then, of course, higher virtualities, you have less space. But the other radius, these, could you comment?
Yeah, so in the
why?
paper, we didn't want to, really, that's the special result, to be honest with you. Okay, so talking to the theorist, if you went to the MIT bag model and you talk to people about it, that's defining almost like the bag size. It's really where the whole matter is extending, and this field, which is scalar, I can't say it's a graviton, so it's a scale. So some people, and this is now a little bit tricky, they say, oh, this looks like the Higgs mechanism. So I talked to Dima Karziev, I talked to that. It's not exactly the Higgs mechanism, but you have this field that extends. That's confining, by the way, right? So it's extending all the way. that field is confining. It has some energy, but it's not the full mass thing. But it's there, and it's generating also, all kinds of effects for these quarks that are zipping around and in terms of generating the energy. And I didn't get clear explanation. That's why I kind of say the most important result from the perspective of discussing a little bit with the theorist is really that we are extracting perhaps a reasonable D form factor for the first time for the gluons. Needs to be confirmed, more data, but the impact for sure of this C or D form factor is the scalar field. That's a very important result.
And what about the contribution to the mass between the two?
I really didn't have time to plot. So I will, these are things that I'm building my talk. Because first I wanted to go to the light cone. And in the light cone, one thing I want quickly, and I'm sorry if I'm taking, look at this thing. By the way, so very interesting if you go to this paper. First, you see this expression of the mass density of gluons. You have the A and the C bar. I don't know how much is C bar for now. So this also a question that we need to deal with. But this, oops, why is it? Yes, this B form factor we neglect. Lattice says it's very small. Everybody I heard says it's small, and if you look, so it's neglected. And then you have this C form factor. If you look at the mass, look where the gluons are, and look what happens. There is a kind of depletion here for these quark contribution to the mass density. So I want to plot the same thing for the scalar. So this is the mass density. If you integrate this, you get the total mass. 2 pi. So 2 pi mu integrated over B perp gives you the total mass. At infinity, at B going to infinity, once your integral goes with the upper limit to infinity, you get M. And I need to do the same for the scalar. It's a special expression. And I will answer your question. Sorry.
So this is, I'm an outsider. I'm trying to get an intuitive picture of what's going on. And I'm sure I'm not the only one. So I would like to ask this.
Yeah.
The simple explanation as to why you are looking for quarkonium threshold is because if you collide a light ball with a heavy ball, the light ball just recoils, and quarkonium is a point-like state for compared to the size of the proton, so you're only the proton internal structure. I mean, is that, did I get it correctly?
Yeah, so it's a dipole. You need a dipole for sure, right? And you need a dipole that's small enough in size so that you can actually probe the system you are after, and that's your nucleon. So in terms of weights,
why do you need a dipole for the quadrupole?
It's color neutral. I cannot do elastic scattering of a color charge on the system. Then I could measure color, but I don't think that would be possible. So the first thing you do is you say, okay, 2 of them, I don't violate any conservation laws in the exchange. And now the question is, what quantum numbers are you exchanging? And what are the possible quantum numbers? In this case, these matrix elements, you are really probing the matrix elements of component of the energy momentum tensor, and one of them looks spin 2, it's 2++, and the other is a 0++. So I cannot even think about it as 1 gluon, 3 gluons, 5 gluons. That was the other model, which they might have a way, and they are working on it to discuss it in terms of multiple gluon exchange. But this is like exchange of lumps of gluons.
Thank you very much. I'm afraid we have to move on because otherwise we take too much from the coffee break. Thank you very much. And
One is the laser.
The laser is the one. Yes.
Mhm.
Yeah, and forward, backward.
Let's see if I remember.
Yeah. Okay.
Her. All right, so thanks very much. Let me thank the organizers for the opportunity to be here. Not my first time, even in CBBF. I had a colleague here. I visited often. It's good to be back. So the talk is about something we call gluon saturation. And I'll try to motivate it. And if you notice, of course, being in a Light-Cone conference, I also put in light front. But I'll make a connection. I won't, some of the calculations we do actually are done in both ways. And one of the few cases you can check one against the other. So since we had many Caprinias last night, let's start very slow. And some things that we all know and hold dear. So the context is mostly deep and elastic scattering. And the relevant quantities for me will be what we call the photon virtuality, which is like in a sense, the resolution of the microscope, which we use to look into what's inside a hadron. The top part, all very well understood. The bottom part, the QCD dynamics for this sort of unpolarized scattering can be summarized or put into what they refer to as structure functions. Now, extremely important kinematic variable for me will be the so-called Bjorken X. You've seen it many times. And I want to emphasize now that it also turns out to be the fraction of the hadron energy or momentum carried by individual parton. So that X is really, if you don't follow any of what I say, remember X small, good. So one of the pleasant surprises apparently from Hera was this nice behavior you've all seen, the fast growth of the parton distributions as you go to very small X's. And you see that it's predominantly gluons. By far, they are the largest, and eventually you have C quarks. That is very important, and we'll be using that effect or that phenomena. Now, all these parton distributions are measured in, let's say, deep and elastic, Hera, elsewhere. But then to use them, you really need this sort of a formalism in PQCD that goes under the name of collinear factorization, extremely powerful. But I do want to, sometimes this approach has been so successful and in a sense, very universal that we use it all the time and we tend to get complacent. Of course, in a conference like this, you all know that this is not all the story. There is a lot more than collinear factorization. But let's remember how it works. If you can prove it for a given process, and it's very hard to do only for very limited cases, it's been done rigorously, then this whole, let's say you produce some, let's say inclusively some hadron, this whole complicated process can be really cleanly separated into stages, if you wish. In other words, proton being a super complex object with millions of things in it, you can ignore all that, say, okay, I'm fine if I just reach out and take one parton from one proton, another one from the other proton, collide those partons, standard PQCD, and then produce a bunch of stuff and the remnants of the protons, and eventually the parton, one of them will hadronize, you'll measure something. All these processes, all these stages are independent. This is really a convolution of probabilities, if you wish. Now, the good thing about this universality, these parton distributions are universal. And the good thing is the partonic cross-section can be calculated if you're motivated enough to any order in the coupling constant. Nevertheless, this sort of a thing is good or rigorously valid only when the hard scale, in this case, say, transverse momentum of the produced hadron, is infinitely large. Now, any real collision happens at finite PT, which means there are power suppressed corrections to this formula. And those can be important because they can have dependencies on, if you're a nuclear physicist, on the nucleon number. If you are a fan of small x dynamics, there could be x dependence here. So in principle, this sort of a factorization cannot be true everywhere and it will break down. The important part for me will be the role played by small x gluons. So of course, this is super powerful and it's been applied to many processes successfully, for example, here. But let's remember that production cross-section is dominated by low PT. So bulk of QCD matter is produced at low PT, we all know that. And eventually at some point you cannot really do collinear factorization. But the more relevant to my talk is kinematics. If you look at this relation, if you produce a hadron with some given transverse momentum and rapidity, and I won't distinguish between pseudo and real rapidity, think of it as the azimuthal angle with respect to the beam axis. When you go to very forward rapidity production at PTs, which are not large, very high center of mass energy, X, this is the parton X in the projectile proton or target proton you probe. Then you will be probing very small X configurations of the hadron wave function. Right? So as you go to high energy, you're going to small X as long as your PTs are not high. And in this context, since collinear factorization is good for high PT processes, of course, oops. No, I am going the wrong way. So of course, in this context of collinear factorization, our parton distributions evolve. They depend on the scale. As you go to higher scale, there's more and more. But it's important if you think of this scale as the inverse size, hadron is a dilute object. The partons, there's many of them, but they don't really feel each other. That's why collinear factorization is good. So this will also break down. So let's now move on to smaller X. Where else the small X phenomena become important or relevant is, for example, if you're doing high energy heavy ion collisions, if you're a fan of quark-gluon plasma, from RIC to LHC, large increase in energy, you have very large window of rapidity. So in principle, you could probe very small X's in the projectile proton or target proton. You go to nuclei, the same thing. You basically probe very small X's. Now, of course, these are high energies, but nature has been kind to us that it provides us with energies even higher, hundreds of times higher. If you go to high energy cosmic rays, there's a whole bunch of them, regardless of what's the incoming thing, proton or light nuclei, and who knows, and we won't get into that. The bottom line is that this collision is basically collision of, let's say, a proton on a nucleon in the atmosphere. So it's like a PA type collision. It's very forward collision. So you're basically probing super small X's in these processes. Now, another context for small X physics is also ultra high energy neutrinos. Again, these are known to exist up to, let's say, GZK cutoff. Again, now here the difference is that you really have a hard scale, Z or W mass. Regardless, the ratio is very small for these ultra high energies. So again, in this context, you'll be probing small X content of a hadron or nucleus. So small X QCD, we basically need to understand how QCD objects behave in this limit. All right, so do we know anything about the small X limit? PQCD already tells us how this growth is happening. It is happening because if you calculate radiation of a parton by another one, so-called splitting functions, they are singular. You see the gluon radiation is singular as 1 over X. X, remember, is the fraction of the momentum. So it's favorable kinematically to radiate gluons or partons which carry a small fraction of the energy. Now, if you have small X's, you have a large phase space, you can radiate more and more. For example, in this particular kinematics, you can show that the gluon distribution grows quite fast. So we know where this steep rise is coming from radiation of gluons predominantly. Now, this sort of idea led almost, I guess, 40 years ago to the idea of saturation by Gribov, Levin, Rishkin, who argued that if you keep your transverse momenta or really transverse sizes fixed and then go to higher and higher energy, in this context, it means going to smaller and small X. Eventually, you'll go from a picture of a hadron with some constituent quarks or a bunch of gluons, the dilute object, to a state which is highly populated, a large gluon density state. This is called the gluon saturation. Now, this is a bit kind of an average picture, a bit of a naive picture. There are fluctuations and so on, but I'll ignore since I'm trying to motivate this. So this is our picture of a hadron or nucleus at high energy, a dense state of gluons. So if this is the case, if this is happening, then remember Feynman came up with this very useful idea of quasi-free parton. That was the whole collinear factorization. Ignore all the complex dynamics of a proton, reach out, take one parton out of it, the rest doesn't matter. Now, if this is really the case, that cannot be true because these partons are now like a collective object, if you wish. They are feeling each other. This sort of a quasi-free degree of freedom is not a useful concept anymore. So one has to come up with some new method, if you wish, or new degree of freedom to describe this state. So this is our departure from standard PQCD. And very often you'll hear, oh, what happens to gluon distributions? Oh, what happens to this? At some point, it's not a physical quantity anymore. So let me try to go there. And I will emphasize that nuclei are extremely useful because this phenomena should happen at nuclei at earlier x's, at x's which are not as small as required for a proton. So nuclei are ideal environment for this. Now, what we would like to understand is this so-called QCD phase space at very high PT. This is the region of PQCD and collinear factorization. Now, if I go in the orthogonal direction, in the high energy direction, I end up with a dense state. How does this happen? What are the behavior of our QCD observable in this limit? Correlation functions, is there some scaling behavior? Is there universality and so on? So one can ask a whole bunch of questions trying to understand dynamics of QCD in this limit. It has practical applications, if you wish. It's useful, for example, for heavy ion people. They try to use this as initial conditions for a possible hydro evolution. Lots of phenomena I can basically investigate using this. So now let's move on beyond the motivation. Is there any evidence? And I'll be the first to say that people are still yelling and screaming and arguing about it. For example, at HERA, and believe me, it's been fought to death. And still, most people say there's no saturation. The only evidence for, not even saturation, for small x need, the need for small x effects is this plot for longitudinal structure function, where you see that there's a need to resum small x logs. That means those small x logs are becoming large and they need to be taken into account. And you see that the behavior at smaller x's really depends on that. So what else? In case of RIC and LHC, there is, you could call evidence, and believers believe it. Non-believers won't believe it. There are other approaches. But I think this is as close to QCD as one can get, especially this. We saw the reference to this disappearance of the dihadron peak. If you think of PQCD, the standard process is 2 to 2. Partonic level momentum conservation means if you have something at 0 degree, you need something at 180. Now, hadrons, of course, there's a bit of a thing, but you see that disappearance between a nuclear target. This is a proton target. You see the peak. Nuclear target, the peak has disappeared. So saturation, people would argue this is evidence for saturation. Nevertheless, it's not quite clear, but we saw these. These are very tantalizing hints, like for example here. So now a lot of the calculations that were done to fit the data or predict the data were kind of a leading order or leading log type calculations. And those are really good for qualitative or maybe at most semi-quantitative understanding. So it's essential that we go beyond that. Now, to go beyond that, you have a problem in the sense that you have a dense state. Now, PQCD and collinear factorization is not going to work there because you don't have one little parton anymore. You have a dense state. What do? So McLaren and Venugopoulos came up with the idea, and they used a large nucleus as a laboratory. Imagine a large nucleus. And the whole time, so this has nothing to do with confinement. So we'll be dealing with transverse sizes which are much smaller than a Fermi squared. So tiny transverse size, look longitudinal direction into the proton or nucleus. If you boost it, of course, you will have your large x degrees of freedom. You will have your small x degrees of freedom. And then there will be a big discrepancy, a big difference between relevant timescale dynamics of the large x partons and small x partons. So they said that the large X partons, quarks and large X gluons, can be thought of as sources of color charge. They carry color. So they are thought of sources of color charge. And those sources of color charge referred to as rho. Now you have a current predominantly along one direction. Of course, that color charge will be, there will be a color field associated with it, radiated by it. So in principle, you can use, or you can solve classical Yang-Mills equations in the presence of, let's say, some fixed color charge, find the solution to classical Yang-Mills equation, and the solution in a particular gauge will be of this form. It will be given in terms of this two-dimensional field, which will depend on this color charge density. So the solution is an implicit solution given in terms of rho. So in this approach, the dense proton or nucleus is treated as a color field. So this is our color field describing our high energy nucleus or proton. Whenever we have a collision, so on one side, I will have this dense state of a proton or nucleus. The other side, what you want, it will depend on how complicated you want your life to be. In principle, one can apply this to what we call a dense system, where both sides are dense states. That's a nucleus at high energy, or even super high energy proton. Then you can't do much analytically. Then people use lattice methods to solve equations in the forward light cone and get some energy densities and number densities and so on. Then the next simplest case, or less complicated case, is what we refer to as a collision of a dilute object, such as a proton, which is not at very small x, bunch of quarks and gluons, on a very dense system. So typical proton nucleus collisions in the forward region. The cleanest process is deep and elastic, because one side photon is quite clean. So I'll focus on this. And of course, as you go from more complicated to less complicated, there is less need for modeling, and the calculations are more robust in the sense of the theory. The essential concept here is what's referred to as the saturation scale, that basically tells you what is the momentum scale at which you have reached this dense state. Momenta above that, you're a dilute state. Momenta below that, you're dealing with a dense state. That has the nice feature that it is dependent on the nucleon number. That's the coherence length, if you wish. Small x gluons carrying a small momentum longitudinal direction, they have large longitudinal wavelengths. They overlap the full longitudinal size of the nucleus. That's the a to the 1/3. The most robust part of the calculation is the x dependence. This number is very, very accurately known beyond NLO, very robust. So we would like to calculate the dependence of our observables on x, or equivalently rapidity or energy. All three are interchanged in this context. Now, since you're dealing with a dense object, if you scatter from a dense object, you have really no choice but to consider multiple scattering. That's part of life. And you cannot really do multiple scattering precisely in QCD. It doesn't, there's some, so you have to make some approximations. Standard approximation is the high energy approximation, old days, Harkanal approximation. So in this approximation, a projectile, take a quark, for example, will go through your nucleus. This is supposed to be going through the target. And because of density, it will multiply scatter iconally each time, and then eventually will go out. The multiple scattering is very efficiently resummed into a Wilson line. So Wilson line is nothing but a path-ordered exponential in QCD, and very efficiently resums multiple scatterings from the target. Now, if that's the amplitude, and I want the cross-section, I have to square. Oh, that's a bad sign. Is it? You scared me for a second. I haven't really started yet. All right, so if you think of this as the amplitude, your amplitude involves a Wilson line, which encodes multiple scattering. To get the probability or cross-section, you need to square. Your correlation function or cross-section is now going to be a Wilson line times Wilson dagger. So the degree of freedom that goes in here is not anymore the standard parton distributions. They don't really make sense in this context. the standard degrees of freedom will be correlators of these Wilson lines, 2, 4 million. And of course, analogous to parton distributions that satisfy some evolution equation, these observables will also satisfy evolution equation, except it's not with hardness or scale, q squared, but it is with rapidity or x or energy. And that equation is known, but it's known as Jim-Walk, and the nicer version BK, and Misha will talk about the latest progress on this. So to summarize this in a sense, we are different from standard PGCD in two important aspects. One is because of high density, we need to include multiple scattering from the target done in the diagonal approximation. Second is rather than doing standard evolution in q squared, our q squareds are limited. They are not very large, but our energy is large, so we need to resum large x, small x's. The genetic effects are this multiple scattering generically, not in saturation, but in general, will lead to PT broadening of the projectile. And when you do the small x resummation combination with this also leads to suppression of spectra compared between a dilute and the dense target. So those are the two main effects. Now, there's been a lot of activity, as you can tell by the dates on these, on calculating next to leading order corrections. As I said, leading order, leading log is good for qualitative, semi-quantitative things. You need more precision, especially now electron ion is coming. And here I will refer to light front quantization. All these calculations are done either in covariant perturbation theory, or in some cases, for example, here, whenever you see BUF, I hope I'm saying the name right, that's light front quantization. The others, including ours, this is covariant. These gentlemen, again, with BUF, this is again light front quantization. So I can do all these calculations in either approach. Light front quantization has a very nice, it leads to a very nice physical picture of what's going on. I have to say that as you go to higher orders, life becomes miserable. I don't think it's the right way to do higher order calculations, but in terms of physical clarity, it's like unbelievable. All right, so, and these are inclusive quantities, a lot of diffractive or exclusive quantities. There's, of course, a lot of work on spin that I didn't even mention. And again, here I will emphasize that, for example, a lot of these work, these guys, they have done it in light front quantization. They have done master normalization. Life is extremely, extremely complicated. All right, so now let's move on to our next to leading order, one particular process. I picked this because the so-called inclusive dihadron or dijet production in DIS, this is one of the golden channels for finding saturation, as Elke mentioned. And it's a very nice process because one side is a photon, it's very clean. So the physical picture here is much more clear if you use light front quantization, you quantize at a fixed x plus. Then what happens is that the virtual photon comes in, splits into a quark anti-quark pair. That's a quark with momentum p, anti-quark momentum q. The pair will go through the target. This thick solid line is meant to be the target. Now, the quark and anti-quark will scatter from the target to all orders. That thick line, remember, is a Wilson line, multiple scattering all order. Now, because of diagonal approximation, during that scattering, the transverse location is fixed. That's the diagonal approximation. There's a bunch of kinematic factors. These are Bessel's basically tell you QED, how photon splits into a quark anti-quark. These red objects defined here, the 2-point functions, those are what I refer to as dipoles. That's the trace of a Wilson and a Wilson dagger. This Wilson line here describes the propagation of a quark at transverse location x1 perp. Wilson dagger describes propagation of anti-quark at location x2 perp through the target. So the observable will depend on this combination. You have several combinations on these dipoles, and also on what we refer to as a quadrupole, 4 Wilson lines. Now you could ask, well, what if I calculate something even more complicated? Would I get even more like sextupoles, octupoles, 200 poles, whatever? And the answer is to leading order in NC, large NC approximation, no. Every process you can calculate in PA, in this sort of a context, PA, EA, EP, only dipoles and quadrupoles contribute. You could do dipole squared, quadrupole squared, but not sextupoles, not octupoles, not those guys. Those exist, but they are NC suppressed. So now good thing is for these are our analogs of parton distributions. How would I get parton distributions from these guys? Remember, these are Wilson lines. When you expand the Wilson line, the first non-trivial term, the linear term after one, those guys will give me the standard parton distributions if I take the dilute limit. Okay. All right, so this is the leading order calculation. Very nice picture. Now, you have to go to next to leading order, and this was done with my former student. We use covariant perturbation theory. People also have used the same calculation in light front perturbation theory. The results are identical. Now, in principle, I won't show you any details except one slide to scare you, but here you can think of this process as a virtual photon comes in, splits in the QQ bar. Quark-antiquark pair will go through the target. That's a thick solid line. And a gluon can be radiated from either quark and antiquark after QQ bar has passed through the target. Or the radiation of the gluon from either quark or antiquark will happen before they go through the target, in which case all three will go through the target. So these are the real contributions. That's like the 3-jet production. Then you have the virtual corrections as usual. Now, again, you have a radiated glue, which can be radiated and absorbed by the same line, either quark or antiquark. For every one, there will be a corresponding one for antiquark. And the 3 partons scatter from the target, or the radiation is inside before they go through the target or afterwards. And the radiation could happen by one leg and absorbed by the other leg. So these are all the combinations. Now, as usual, as you do loop corrections, you pick up some complicated things. And of course, you can easily memorize this. But the essential point is you don't really need to pay attention to any details, except you will see that the same exact degrees of freedom, dipoles and quadrupoles, appear here. And some are beloved vessels that tell you how the photon splits appear. So you can ignore the rest. All right, so of course, those are formal expressions in the sense that they are full of divergences and officially formally don't even really are not well defined. So you get all sorts of divergences, standard divergences. For example, the ultraviolet, where K for momentum K goes to infinity. Real corrections are UV finite, virtual ones are divergent, but there are cancellations between various diagrams. So eventually, everything is UV finite. There is no need for renormalization. You have the standard soft divergences, and by soft, I mean all 4 components of momentum going to 0. Here you have the usual cancellation between real and virtual diagrams. So again, you can show that all the soft divergences are canceled. Then next thing is what sometimes referred to as a rapidity divergence. In this case, I'll just call it the standard small x divergence, in the sense that you have the radiation spectrum of a soft gluon going, like I mentioned, 1 over x, that's the 1 over z. That's of course divergent. So what you do is introduce a very rough sense, a factorization scale along the longitudinal direction, call it that ZF. Now this portion is divergent. The other portion is, if you wish, the finite correction. So this portion here, that complicated expression I showed, you take the limit z going to 0. Then you can show that all of them combine nicely into these red and blue parts. The red parts are actually nothing but the evolution, rapidity evolution of the quadrupole. And the blue part is the evolution of the dipole. So all the rapidity divergences are absorbed the same way that you would absorb a standard divergence in PQC into your running of parton distributions and fragmentation functions. Here, the rapidity divergences are absorbed into small x evolution of dipoles and quadrupoles. And the last class is the standard collinear divergence. So this is happening when your radiation is basically, let's say in the massless limit, radiation is parallel to the parent, the angle going to 0, and this is happening at finite momentum. And this is, if you wish, a physical phenomena in the sense that one has to renormalize the so-called fragmentation function. So you start with a bare fragmentation function, you absorb the log divergence, log q-squared divergence into running of the fragmentation functions. So at the end of the day, that's a summary of all the divergences. So it means that to one loop accuracy, you have proven explicitly that factorization holds. All the divergences are either canceled or absorbed into running of physical quantities. So the physical production cross-section can be written very hand-wavingly, roughly as evolution of the leading order cross-section with rapidity, or evolution of the leading order cross-section with the fragmentation functions to a given order, and the finite pieces that are genuine NLO. Of course, now one can use these to do phenomenology relevant for the electron-ion collider. As LK mentioned, this will be a golden channel. Of course, life is a lot more complicated than this, but let's say it's a golden channel. And can also use it for ultra-peripheral collisions at LHC. That's really nothing but a photon target collision. All right, since time is up, let's basically summarize. But I wanted to basically maybe one extra slide. Our chair is extremely kind, and we will take advantage of that, abuse that trust. So I'll just have like one or two more slides. So I mentioned dipoles and quadrupoles. That's all the dynamics of target at small x. Okay, so QCD dynamics is contained in the behavior of dipoles and quadrupoles. And the question is, how do they evolve with x or rapidity or energy? That will tell us how the cross sections evolve. So it's useful to consider one of them. This is basically a dipole that T is nothing but 1 minus S. Now, Misha will show you a lot of these, but I'll just say that if you understand the behavior of dipoles, you can get a rough idea how the cross section will behave. In the high PT limit, if you take the dilute limit, that's the dilute limit, we get the standard 1 over PT to the 4th partonic cross sections. Now you go to very low PT, below the saturation scale, you're in deep saturation region where the state is a high density state. You will see that behavior has drastically changed from 1 over PT to the 4th. Now this is hand-waving argument, something which is pretty constant, very slowly changing. That change in basically power of 4, that's a prediction of the theory. That's due to saturation effects. In the intermediate PT, for the experts, this is the BFKL region, and the physics is determined by the BFKL anomalous dimension. And these sort of arguments from here, you can show qualitatively that you get all the expected behavior, all the behavior you've seen in the data. So it has all the right features. So understanding these qualitatively basically tells you what to expect. And of course, this is a kind of quick summary. We know that at high PT, we have an extremely powerful collinear factorization approach to particle production. If you go in the orthogonal direction, I've tried to argue that there exists analogous formalism, usually referred to as gluon saturation, color glass condensate, whatever, that we have understood quite a bit. But what is missing really, at least in my mind, is a unified formalism that has both limits built in. That doesn't exist. And I think it's extremely essential to do it. But I will stop here and basically repeat what I said. And I'll just say that electron-ion collider coming up, it will be a very precise machine. It will really probe things that we have seen, we've seen glimpses of saturation, if you wish, but we'll be able to really probe it very decisively and precisely. And for that, we need all these precision type calculations. One I described as the one class of precision calculations, higher order loop corrections. There's a different class that go under corrections to the Arcanal approximation. So that's another avenue of precision. I didn't say anything about that. And these are needed because intrinsically, what the procedure I described, the phenomena are really limited to small x. And of course, in electron-ion collider, you'll have a large phase space, intermediate x, large x. And so it's important to try to kind of unify them together. Thank you.
Thank you for the nice talk. We have time for 1 or 2 short questions. Short.
We'll try. Yeah. At finite temperature, we kind of know that to arbitrarily large temperature, you have non-perturbative corrections, even if the cup, because you have two scales. One is the temperature that can be ultraviolet as you want, but the other one is sort of the infinite volume. And you get, you know, in here, no matter how small x is, you always have this one femtometer, the radius of the proton and the radius of the nucleon. Are we sure? I mean, you've shown it to like one loop, but at finite temperature, infrared divergences come up at 3 loops. Are we sure that there is no non-perturbative physics really hiding at small x?
There is
In the same
definitely
analogy.
non-perturbative physics even at small x, absolutely. However, of course, I cheated a little bit or a lot, because all I described is really good. Remember, I mentioned this Maclaurin's idea that you look at a large nucleus, and I did say that you really have to restrict yourself to very small transverse areas that you're not sensitive to confinement. As long as I'm allowed to do that, that means P or scales, either QS saturation scale or the PT involved, has to be much larger than lambda QCD. Now, this is okay as long as my saturation scale is large. But one thing I cheated, or many things that I cheated, was, remember I showed you the dependence of saturation scale on many parameters. Now, here. Now here you could have totally picked on this and say, well, are you solving confinement? And of course, the answer is absolutely not. Where does that come in? So this one, conveniently disregarded, is there is impact parameter dependence here. I have to stay with very small impact parameters. And if I do, then I'm okay. I'm not sensitive to confinement. Now, the theory, especially if you're a BFKL fan, the theory is sick at large impact parameters. So now the real question is, should I believe your results at small impact parameter? How do I know that the large impact parameter is not ruining your small impact parameter calculations? In principle, if you're in the deep saturation region, you can show, and people have done this calculation, but again, fixed order perturbation theory, that your color neutralization scale is of order of QS, so you don't become sensitive to confinement. If you're asking about the hard thermal loops, there is none here. So that was my cheating. So we really have to stay at small impact parameter.
Okay, I'm sorry we have to move on. Thank you again. Now we have Misha Rublinski giving his talk. Very good. No, this is the laser. Okay. Forward and backward. Very good. Oh. Oh.
Okay. Okay. Good morning. So I will follow the talk of Jamal, but a little bit more on formal side. It's largely based on my very long collaboration with Alex Kovner for the last over 15 years. We wrote over 40 papers together. So, and Vladis Kokov. So I will start with most of the talk will be more introductory, but not very easy. And then towards the end, I will tell you the latest developments. So our approach to high energy scattering is basically based on light front formalism. We consider a collision of two hadrons. One we call targets, another one we call projectile. Each of them is supposed to be an eigenstate of light-cone QCD Hamiltonian. so we collide them, and then basically we have a Hilbert space, which is just a direct product of a projectile and the target Hilbert spaces. We want, for example, to consider a total S matrix for the process. So we have to pick a second quantized S matrix operator and sandwich it in the projectile and target wave functions. So that's would be the goal. So we assume that both wave functions are parameterized by charge densities, color charge densities, which are called rho p here and rho t. Basically, these are just zero plus or minus components of the vector current, which could be made of quarks or gluons. Mostly we talk about gluons, of course, at low X. So this object we don't really know how to compute because we don't know the wave functions. We would love to know the wave functions, but we are not there yet, and maybe never will be. So more generally, we can consider any hadronic observable, just like Jamal was mentioned, single inclusive, double inclusive gluon production, any observable on the Hilbert space could be computed this way as a matrix element of this of relevant operators sandwiched in the projectile and target wave functions. Again, we don't really know how to compute these objects, but what we hopefully can do is we can answer the following questions: how these matrix elements change if you a little bit increase the energy of the scattering process. So at a given scattering energy, we cannot compute, but if we just a little bit increase the energy, then we can show, it's pretty universal statement, that all these matrix elements, including S matrix, actually evolve according to this Schrödinger-like equation with some universal Hamiltonian, which basically represents the effective Hamiltonian of high energy. Oops, wrong. I'm lost. Of high energy QCD. This is actually holy grail of the entire program of reaching and understanding high energy QCD, is basically to come up with this Hamiltonian. In the old days, in 60s, it would be called region field theory. But today we really don't talk about regions. We mostly talk about Wilson lines. We believe these are right degrees of freedom, and we want to write a universal Hamiltonian. So how would we try to derive it? Okay, I say we need to increase the energy of the process. So we could increase the energy by, say, a little bit boosting the projectile. So if I a little bit boost the projectile, nothing happens to the target, but wave functions of the projectile changes. And as a result, this inner matrix element, just S matrix, for example, we'll focus on S matrix, sandwich in projectile wave function will slightly change. So let's zoom on this matrix element and see what happens. So I will call it sigma, and after the boost, increase rapidity of my projectile. It will evolve with this evolution operator. It's like it's evolution operator, but in Euclidean time, which is rapidity. Oh, how I'm lost with this pointer. So, and we can compute it in perturbative QCD. So with Hamiltonian, and it admits expansion in alpha S. You have a leading order, and you have next to leading order, and so on. And it's fully fledged Hamiltonian. It's quantum mechanics with Hamiltonian X on the, now this is a matrix element. So there is no trace of projectile any further, but it's a Hamiltonian that acts on the target Hilbert space. So, and G-walk, which was already mentioned by Jamal, is a specific limit for which Hamiltonian, when the projectile is actually dilute, but the target is assumed to be dense. So we allow linear gluon emissions in the projectile, just like BFKL emissions, and multiple rescatterings on the target. This is where the shock wave or Wilson line come in. And if you apply this gym walk to the dipole, which Jamal again mentioned, you in the large NC limit, you recover the pretty famous Baletsky-Kovchegev equation. So the history here is the following. The linear order gym walk was derived particularly by Jamal over 20 years ago. It took nearly a decade to come with analog Hamiltonian, which I will show for you today just to scare you a little bit. And when we got mass corrections to this Hamiltonian a couple of years ago. So the progress here is basically every significant step takes about a decade to reach. And I will try to tell you in few words where we reach over the last 10 years. Now, well, it's not a review, but what's happening now. So let me start with really motivation and objectives. It was already emphasized, particularly by Jamal. We badly need precision phenomenology for saturation physics at NLO accuracy. And it's not exactly there yet. Otherwise, people will, we will, for decades, we are running like saturation models, leading order calculation, saturation inspired ideas, but we need precision phenomenology. And fortunately, by now we have an NLO Hamiltonian. So in principle, you have the Hamiltonian, just run it and do your pheno. But there are some problems here. And one of the problems is actually, even when we have a Hamiltonian, we don't know how to solve it. We even didn't know how to solve the leading order Hamiltonian, but we learned to do it numerically, using some stochastic approaches based on Langevin reformulation. But at NLO, it's impossible to do it. At least there is no progress here yet. But there are also additional conceptual problems, which is what occupies me over the last years. And not only me, of course. There appear large logarithm at NLO. So it's very schematic, and I will be more absolutely exact in the following slides, but schematically, just to give you the flavor of what's going on, the Hamiltonian looks like that. You have alpha S leading order times something, it's a kernel. I will show it to you, it's a Jim-Walk kernel. And then next to leading order, you have another alpha S times some generic NLO, we have another generic term, generic NLO term, plus some logarithms. So there are many logarithms, and some of these logarithms are usually associated with some transverse momenta, the ratios of transverse momenta, and some of these logs could be very large. And once this log is large, you may reach the situation alpha S times log is of order 1. And once alpha S times log is of order 1, you cannot claim this piece to be analog, some alpha S perturbative connection to the leading order. And that means you have to resum all these logarithms. Okay? So basically, even when we have an analog walk, it's useless without resummation. So, and there are plenty of different logs. Some of them are UV divergent logs. We understand them as running coupling effects, and part of my talk is related to this topic. There are effects which are related to time ordering or Joffe time ordering. And there are logs which are related to D-glab splittings when one gluon splits into two hard gluons when you have large momenta. And what the task actually is to identify all of these contributions, clearly separate what goes into running coupling, what goes into Joffe time, what goes into D-glab, and then independently resum. That's a program which started about 10 years ago, and it's still running. And basically, I wanted to flash, that will be the end of my talk. But basically, we in the paper which we put on the archive barely 3 weeks ago, we have achieved what I believe a major progress here in this program. First of all, we did manage to understand what's the right running coupling prescription for Jim-Walk and the scale of running, and that's something which we would refer to RC Jim-Walk. And we also managed to derive an RG improved G-involved Hamiltonian. So you basically run RG evolution in the space of Hamiltonians. And this is why we basically wrote down something like a D-glap in operational form, which acts on the space of Hamiltonians. And we even managed to solve this RG flow in a couple of limits. One is a dilute, BFKL-like limit, and one is deep saturation limit, dense limit. And the bottom line, that what this RG does, it smears the kernel of the leading order. So this is just an announce, just because, before I lost some of you, hopefully not, but that's what we did. So now I will start with basic introduction, but more technical about how we actually derive G-involved evolution, what's leading order G-rock, what's next leading order G-rock, and when were the problems and how we solve. So the start is simple. As I say, the projectile wave function. I press one button, it works as another button. So it's a Born-Oppenheimer approximation for the wave function. So the wave function is eigenstate of QCD Hamiltonian. It's a full QCD Light-Cone Hamiltonian. The wave function is just a bunch of Fock space components, which we order here in K plus. This is a longitudinal momentum. We assume some cutoff. And we separate the modes. So that's a usual Born-Oppenheimer approximation. We split the mode above the cutoff. We call them valence. They are fast modes. These are blue ones. And then below the cutoff, the modes are soft. We have very small K plus. The valence modes above the cutoff act basically as a charge current, or which is lives on a shock wave. That's the structure of our wave function. We don't know really the distribution of blue gluons, but what we may be able to do is to compute the distribution of soft gluons which sit below the cutoff. Why soft gluons are important? Because assume that all the gluons above the cutoff scatter on the given target. That's my implicit definition of the cutoff. The cutoff will never enter any calculation eventually. What happens if I increase the energy? I boost my wave function. When I boost Light-Cone wave functions, all the modes moved up. Okay, K plus scales up. So the modes which used to be below the cutoff now re-emerge above the cutoff. So they will now start to contribute to the scattering. This is the reason the wave function gets changed and the S matrix gets changed as a result of this evolution of the projectile wave function. So we need to know the physics below the cutoff. And in order to do that, we basically take the Light-Cone Hamiltonian, we split it into three terms. The one is the valence Hamiltonian, which I have no clue what it is. There is a free part for these soft modes, which are denoted as A. And there is interaction of soft and valence. And what we are going to do perturbatively is basically to diagonalize this part of the Hamiltonian in presence of some valence modes, which we don't know. That's, again, usual Born-Oppenheimer idea. So we assume that this wave function before the boost is actually a vacuum of the soft modes. So it's eigenstate of the valence part of the Hamiltonian, and I don't know this state. So we are doing perturbation theory around state which I don't know, but I can, but I can compute how it changes. So, and then I introduce these soft modes. We dress my valence state with some dressing operator Omer, which essentially diagonalizes this part of the Hamiltonian. So this is a usual perturbation theory here. And so this is what you do at leading order. It's pretty trivial because the Hamiltonian, the interaction Hamiltonian between valence and soft at leading order is just linear coupling between, okay, you recognize here, it's actually free gluon vertex. Rho is a current. It has two gluons inside. But in leading order, because of the separation of scales, or our splitting of degrees of freedom into hard and soft. This is basically iconal approximation or iconal coupling inside the triple gluon vertex, and you pick this k plus to 3/2 here. That's what is left from the triple gluon vertex. And this Hamiltonian is linear in A fields. And once it's linear in the A fields, it's very easy to diagonalize this Hamiltonian. And the operator which does it is this coherent operator, which diagonalizes linear interaction. And B here is the Weisaker-Williams field. And so it's actually classical physics what I'm talking about. You find it in Jackson. It's emission of charged particle, emission of soft radiation by charged particle. Classical Leon, there is no QCD here essentially. A part of the color index A which appears here, it's really classical electrodynamics in this soft radiation limit. Now, how do I, from that I get, in one line from that I get Zimwalk equation. Okay, let me finish the sentence first. So this is a wave function, and you remember I need to square my S matrix inside this wave function. So basically I have two omegas from two sides, and all what I need is to tell you what the S matrix operator, and for S matrix operator, we basically take this Wilson acanal scattering approximation that Jamal mentioned. Every particle which goes through the shock waves basically picks up a Wilson line. So you expand this to leading order in G, you get one G from here, another G from the conjugate amplitude, you square S matrix and you get the Zimwalk Hamiltonian. This is a leading order Zimwalk Hamiltonian. You get this, basically these are free diagrams which contribute to this Hamiltonian. This is a shock wave, as also Jamal showed. This is a Wilson line for scattering on the target, alpha T here, target field. And this is a diagram corresponds to this term. This is a kernel, this is BFKL kernel of Weisaker-Williams kernel, which appears here. And I introduce, instead of rho, which appeared before, I introduced J left and J right. This turns out, I will not go into details, but these operators, charge density operators of the projectile on the target space, it turns out we act on the Wilson lines of the target space, and we become left and right rotations on the Wilson line. So this Hamiltonian is indeed quantum Hamiltonian. Is the degrees of freedom here S, and J's are conjugate. We are not really canonical variables, but this is an operator which works as a Lie derivative actually on the Wilson lines. So this is a Zimwalk Hamiltonian. It includes all the physics of BFKL, including so-called BKP evolution, triple Pomeron vertex of Bartels, everything which people knew about leading order BFKL is included in this compact form. So next to leading order. At next to leading order, you have to compute many diagrams. So at next to leading order, you have stuff when gluon emits and then splits into two quarks. You have instantaneous emissions. You have double emissions from two different valence charges. Gluon emission splitting. And a bunch of other stuff like these diagrams, like loop corrections. This will contribute to running of the coupling, and all that in Hamiltonian light-cone perturbation theory. Order of emissions matter. So this diagram and this diagram, even though topologically they look the same, it's actually two different diagrams in light-cone perturbation theory, Hamiltonian perturbation theory. And a bunch of this stuff, all that you have to compute. And then you have, And then this is the structure of your wave function. And you have to take two of us, squeeze inside shock wave, and compute the Hamiltonian. And it takes 3 years to do. And then I will not scare you with details of these calculations. But anyways, once you square, you get various type of contribution to this S matrix element of the over the projectile. This line looks like the leading order, but there is a complicated vertex here, which we computed. You have two quarks going through the shock wave. You have two gluons going through the shock wave. Some nonlinear terms in the charge densities. This is a new stuff. You have a bunch of this type of diagrams. They mostly contribute to iteration of leading order Hamiltonian. You have to carefully subtract what is just second iteration of leading order and only what is new to call analog. Once you have done, you write down this Hamiltonian, which now looks a little bit more scary. The first line reminds you the leading order Hamiltonian. It's precisely the same structure as the leading order Hamiltonian, but now you get a more new kernel which appears here. And when you have, I mark in blue what is actually relevant for my today's talk. So this guy comes from an emission of two gluons, which went scatter through the shock waves. You have two gluons here. And you have two quarks in Wilson lines in fundamental representation, which go through the shock wave. And then you have the bunch of nonlinear terms, which are really not relevant for today's talk. So I just didn't want to cut the Hamiltonian, so I flashed it fully here. Now, let's have a look at these kernels. So capitals are just differences between position. It's all done in position space. So the contribution, which is due to two Wilson lines, two gluons, is here. You are not supposed to pay too much attention to the exact expression. It's alpha S squared. There is another term which I didn't even want to show because it's irrelevant for today's presentation. For JSJ, that's the one which appears in front of the leading order. It's a correction to the leading order Hamiltonian. I wanted to draw your attention to these terms. And B here, this blue B here is a one loop coefficient of one loop beta function. Okay, and that will be central for my talk today. And you see these coefficients multiply a couple of logs. These are the logs I have been talking about, which might be nice. This mu here is UV cutoff. That's because you have to get rid of by renormalization of the theory. It's a divergent log, and this one you naturally absorb in the running coupling. And but you also have terms which also proportion to the beta function. Or coefficient of the beta function, but you have log, which is absolutely finite in principle. You integrate over all these coordinates x, y, z, and z prime, z and z prime are the positions of two gluons. But it could be absolutely large because once you integrate independently of x and y, the ratio can be very large, and that can produce you something problematic. So these are the logs which I want to take care of. Okay, my goal is to resum these logs because we are nasty. We completely destroy the analog, the alpha S expansion. You cannot do phenomenology with this stuff once you have large logs inside. You just totally spoil any attempts to do something useful with this stuff, with these kernels. So. The goal is let's focus on this correction to the leading order kernel. So this is again leading order kernel operator, which with some kernel which in principle has the leading order part plus this KJSJ correction which I just flashed. Just more like a remark, if you take this operator, you act on the dipole, and dipole is a trace of two Wilson lines as Jamal introduced. You get this BK-like, Baletsky-Kovchegov-like evolution. And for this kernel, dipole kernel is related to this kernel by this expression. That's general relation. And this kernel here must be positive semi-definite, which means this integral for arbitrary two functions f must be non-negative. one of the consequences of this constraint, if it's not the case, this Hamiltonian is completely sick. It means it may have negative eigenvalues. It will not be corresponding to any reasonable physics. So one of the constraints coming from here is this combination, which is nothing else by this dipole kernel, must be always positive or non-negative. There is a more stringent constraint, which is kind of new observation which we made, that also this combination for arbitrary x and y coordinates must be non-positive, and I will tell you in a second why it's important. So there has been back to this correction, analog correction to the leading order Hamiltonian. We have this couple of logs. I'm only flashing you log terms, and I'm completely ignoring all the rest. These are terms proportional to B. What people did in the past, and there are a couple of classical works, one by Baletsky, another one by Kovchegev-Weger. So these are classics because they already appear in textbooks. These results. What these people did in somewhat slightly different schemes, everything which you see which is proportional B to B, you dump into some form of alpha S running, because you assume this is beta functions, this is coefficient beta function, so it has to do something with the running coupling. And when you come up with some very strange nasty expressions, for example, here you have alpha S of x, alpha S of y. Here I'm very sloppy, I call alpha x of x, I mean x square inverse of x square, of course, okay? It should be, of course, momentum scale, but it's easy to translate it into momentum scale, divided by something else. So you come up with, oops, once again. You come up with some strange combination where I have alpha S in the denominator, which is strange, but otherwise, and so the way you cook this up is just, if you expand back to alpha S order squared, you should reproduce these logs here with the right coefficient. And you cannot just do it simply, you need some very complicated structure. And what we are showing in the paper is a forthcoming paper, which will be released on a 1 week scale. But all these kernels are also sick. We are not positive semi-definite. Basically, we are wrong in simple words, okay? So we should do something else. Let me tell you what we need to do else. Oops, I'm wrong again. So we basically have to do 4 steps. First, we have to identify the right observables. The right observables. So the right observables, and that demands us to realize that gluons split, but somehow, not always we can resolve this splitting at NLO. So we need to introduce resolution scale. Once we introduce resolution scale, we basically have to replace bare gluons into dressed gluons, bare Wilson lines into dressed Wilson lines. And I hope, if in the remaining 30 seconds to show you how we do it, then you have to clearly identify what you attribute to running coupling and what goes elsewhere. And for that, you have to zoom on the UV divergence. Then you have to resum all the UV divergence log into running coupling. And we come up with unique, well, wrong, not really unique. To get it unique, you need to go to NNLO, which nobody is there. But this most trivial prescription for the running coupling, and it's positive semi-definite, it's a good prescription, healthy one. And it really corresponds to what we see. And then you have to identify the remaining logs. We see with the remaining logs, they depend on the resolutions KK, and we can clearly see they come from deglap splitting, which we know to resum. And then the kernel will also get some correction, which goes as a K deglap. Let me see what I can tell you. I will skip this. Okay, let me just tell you how we introduce the dressed Wilson lines. Basically, this is your bare Wilson line. And now you have, D I introduced here, but I skipped it. This is just double scattering of two Wilson lines. this is a splitting, almost a de-Glob splitting function. This is something which you see inside the calculation in the NLO, but we really want to zoom in onto these pieces. And we notice that once you integrate the splitting function, of course, we are not the first one to notice that, it's again in the textbooks, that once you integrate the splitting function, you get this B. So the first coefficient of the beta function does not only belong to the running coupling, it's actually related to the de-Glob splitting function. And so once you do that, it's almost a splitting function, but I will skip the comment. Let me just fast run forward. Basically, what you do, if this term is big, basically you have to iterate it. If one gluon splits into two, then the daughters can split further and further and further. You can build a partonic cascade, de-Glob cascade of these Wilson lines. And contrary to the usual de-Glob, we allow both gluons, which are daughter gluons, to scatter. In normal collinear physics, once you have emission, only one parton scatters all the time. Okay. Here we allow all the partons which emerges as a result of the splitting to scatter. This is why your de-Glob appears to be functional. And basically, here is a functional equation which we want to solve for the Wilson line. And then you basically plug this Dres Wilson line inside the analogy walk. And there is, you close this equation. You have to solve it by iteration. This is a functional RG. You have to make sure the entire Hamiltonian at the end of the day doesn't remain depend on the scale. That's exactly the same as you do in de-Glob. You have coefficient function, you have parton distribution, both depend on the scale. So the analog here is but we do it for the Hamiltonian, not for parton distribution. The Hamiltonian itself acts more or less like TMD, like the rest distribution. So you sum alpha S, as I already advertised this result, and then that's more or less you get basically the evolution, the formal solution for evolution. You start from some seed Hamiltonian, which you define at some scale which is associated with the projectile, and when you evolve to the saturation scale which is associated with the target. There is a important difference between scales, saturation scales on the projectile and the target. If you are in dilute on dense case, which is what GenWalk is supposed to be, this is a large evolution, so it's important. This is a formal de-Glob operator, which is functional, which acts on GenWalk Hamiltonian itself. You may solve it in a couple of limits. Here I even skip. One is dilute, you just expand everything in alpha, that's BFK-like. The point is this de-Glob becomes homogeneous, and this is why you can solve. You can solve in dense limit just by ignoring these nonlinear term, and then again it's solvable. Let me flash you the conclusion. Sorry, I knew that I wouldn't make it. So I just wanted to give you the flavor of what we are doing. So let me only tell you the summary. So we managed to derive a de-Glob-like summation inside the GenWalk Hamiltonian. These corrections are important. Again, that's what I tried to flash in the last minute, because these corrections run evolution between typical correlation scale in the projectile, which may be saturation scale in the projectile, or color neutrality scale in the projectile, which is supposed to be very small, up to the saturation scale of the target, which is supposed to be very large. That's precisely where GenWalk physics is applicable. This is why this summation is mandatory. Now, the effect on the kernel, if you zoom in at the results, for that you should go to the paper, you see smearing of the Weizsäcker-Williams fields, which appear in leading ordered Hamiltonian. we have more or less unique, or at least it's very natural and good prescription for the running. Instead of fixed alpha s, you have running, basically a renormalization of the charge in the project, in the amplitude, and separately in the conjugate amplitude. And we have not even started yet to do any phenomenology. Let's next decade. Okay, thanks a lot for your attention. Sorry for being late.
So you're late, and it's not your fault. It's not completely your fault that we are late now. It's also on me. We are about 20 minutes late. So we should be coming back right now, actually, after coffee break. But I suggest we have a 20 minutes coffee break and be back at 11:20. Okay. Oh. I haven't decided yet. I think I could go to the bank to get some money because I haven't got any money. So I can't pay for the bank. Car. Well, that's good. I have to get cash out of the money machine. Some money. Yeah. So I have to do. No, I don't. Somebody should go. No, maybe have. Somebody should go. You have some machine somewhere. No, I'm going to be using my ATM card. Yes. And then. Let's see. Yeah. Yes.
Hello. Yes. Okay.
Yes, the laser is here. You have to press. Takes a while, but it goes.
Okay.
It's forward and backward. Okay, so I think you can start. The next talk will be given by Dr. Chandan Mondal. So we have 30 minutes.
Okay. Thank you. Good morning, everyone. So, first of all, I'd like to thank the organizer for the invitations and giving me the opportunity to present here. So today I'm going to talk about glue and see inside the proton from a light front Hamiltonian approach. So we know the proton is a complex system. There is not only 3 valence quarks, there is a sea of quark and gluon. So they provide some rich structure of the proton. So today I'm going to talk about basically the various kind of distribution of gluon and sea quark inside the proton from light from Hamiltonian approach, and this work has been done in a collaborations and between this basically Iowa State universities and IMPCS. So all the results obtained by our students, postdocs, and our colleagues. Okay, so my talk has been divided into basically 4 parts. First of all, I'd like to introduce what are the importance. Why do we need this gluon and sea quark inside the proton? And then I'll discuss about our theoretical approach. It's a non-perturbative approach known as basis electron quantization approach based on Hamiltonian formalism and its application to the proton structure and how can we calculate the proton. And when we consider in the first part of my talk, I'll consider the 2 Fock sector where we have this leading Fock sector and 1 dynamical gluon in this picture basically. Since we have the gluon in this Fock sector, then we have this opportunity to study the gluon distribution function inside the proton. And the next part of my talk, I'll discuss about the sea quarks when you include another Fock sector in additional Fock sector, which is like 5-particle Fock sector in this additional to these first 2 Fock sector. And I'll discuss about the sea quark distributions in the proton. And finally, I'll conclude my talk and I'll give some outlook. Okay, the first thing is that two fundamental properties, mass and spins. So these are the 2 most fundamental properties. Basically, we know that whatever the visible mass, we can see the 99% of the mass is contained within the nucleus, basically. So basically, proton is made of the quark, and inside the nucleus we have proton and neutron, and in a nucleus is sitting inside the atom, and all the mass basically contained within the nucleus. But the point is that the proton and neutron, they are made of almost massless quark. The current mass is like 5 or 6 MeV, and massless gluon. The question is, how does this 99% mass emerges for the proton mass? Proton mass is around 1 GeV, but we have like 1% of this nuclear mass is coming from the quark mass. So here is the story. Basically, the gluon play the role. The gluon dynamics generate this rest of the mass, we can say. Other important properties is the proton spin. We know this proton is spin of particle, but the qualitative decomposition in terms of quark and gluon degrees of freedom, that is not fully understood yet. From the experimental point of view, we know around 25% of proton spin is coming from the quark spin, but still we don't know the sea quark contribution here. And the gluon contribution will contribute around 40%, but there is a question because this gluon contribution is not well measured at the low X region. There is a huge uncertainties in small X region. And the other part is the orbital angular momentum contribution from the quark and gluon. That is also not well known from experiment. There is no experimental data at all. but there are some theoretical calculations. So we know some knowledge, but from experimental point of view, we don't know anything about this part. So to understand these two fundamental properties, proton mass and spin, we have to understand the thermodynamic force between the quark and gluons, and we have to understand the internal structure in terms of quark and gluon. Okay, so this is another slide. So before 1980s, we thought that from the non-restricted quark model, the proton is made of just 3 valence quark, and all the quark contribute to the proton spin. But this is not true after 1980s. We came to know that only a tiny portion of the proton spin is coming from the quark spin, and then the proton spin is then the puzzle is come into this picture. So basically, this is not the true picture of the proton. Proton is basically, there are a lot of things, lot of quarks, lot of gluons. So they have the gluon spin also contribute, and they have the orbital angular momentum. So this is the real picture after 90s, the present situation. So we have to understand, to understand the proton spin, we have to understand the gluon spin as well. Okay, so there are 2 famous decompositions. One is the frame independent decomposition, so proposed by Professor G. So it's like if we decompose the proton spin, it can be decomposed in terms of quark spin, quark helicity basically, and quark orbital angular momentum, and the total angular momentum of the gluons. And they can be obtained, the total angular momentum can be obtained through GPDs, which are accessible in like DVCS or vector meson productions. On the other hand side, the polarized part, the gluon helicity, the quark helicity, that can be obtained from the DIS, polarized DIS scattering. On the other hand, there is other famous decomposition proposed by Jaffe Manohar. It's like frame-dependent quantity decomposition. So the total angular momentum of the gluon can be further decomposed in terms of quark and gluon. So to understand this orbital angular momentum, this is a twist-3 quantities, and to calculate this quantity, we have to calculate the twist-3 GPDs as well. So the point is that from the there is a recent review that says that the quark contribution to the proton spin is around 42%, while the gluon contribute around the 38%, and the C quark contributes like 3%, and the D quark is like 10%. And from the lattice calculation, it shows that at some higher scale, this gluon contribute around 0.3. So this is already talk. I mean, there are many talk on this of the tomography of this hadron. So I'm not talking about this again. So the point is that we have in our calculation to understand the proton spin and proton mass, we have some approach, theoretical approach known as basis light from quantization approach. It's a non-perturbative approach, is a computational framework. So the idea is that if we know the light from Hamiltonian of a system, we can solve the time-independent Schrodinger equations. And by solving this eigenvalue equation, we obtain the mass spectra, the eigenvalue correspond to the mass spectra, and the eigenvector that correspond to this basically this the light from wave functions. So the basic input is that we have to know the light from Hamiltonian that can be derived from the first principle calculation from the Lagrangian itself, or it can be effective Hamiltonian. So our aim is to obtain the light from wave function of the bound state. That once we obtain the bound state or light from wave functions, we can further it contain all the information, structural information about the bound system that can be used to calculate the 3D imaging. Basically, we can calculate the GPDs, form factor, TMDs, all kind of distributions encoded in the light from wave function, and we can also investigate the spin structure. Okay, so now the idea is that first, what do? We expand the baryon state in terms of Fock space basis, and then we truncate at some point. Let's see if we consider the leading Fock sector, we have the three particle state, and for each particle we again use some basis function to identify each state. We use in the transverse direction, we use like plano harmonic oscillator basis, where we have the 2 quantum number n and m. And in the longitudinal direction, we use like plane wave basis. That is, the longitudinal quantum number is defined by this k. So since we have this many particle Fock sector, so for many particle basis, we have to use like this is a direct product of single particle basis state basically. And in principle, for the computational purpose, we have to truncate the infinite basis space. First of all, we truncate the long fork space. Then for each fork sector, we have another two kind of truncation, so which is defined by n max and k. So if we increase the n max and k, that is basically that provides the high UV cutoff and lower IR cutoff. So if we increase our basis size, basically the size of the matrix we want to solve. So that is the overall idea about this BLFQ. So the story began in I think 2020. Once this is the first application to the nucleon, BLFQ application to the nucleon, where we use some effective Hamiltonian. By in this case we consider just the leading fork sector, where we have just three quarks, and we consider this kinetic energy term, and there is some confining potential. The transverse confining potential is adopted from the Light-Cone holography. It looks like harmonic oscillator type potential, and this complementary potential in the longitudinal directions. This is this in the non-relativistic screen limit. It also provides some kind of harmonic oscillator potential. So basically, we have like three-dimensional harmonic oscillator type of potential confinement, and to generate the spin structure, we have also like we included the one-gluon exchange interactions. So this is for this leading fork sector, where we have the three particles, and we solve this eigenvalue equation, obtain the wave function, and further employ to investigate various properties like form factor, PDF, or angular momentum distribution, GPDs, TMDs, and even this Hamiltonian has been further employed to this lambda and lambda C system. Recently, we are preparing to draft basically these gravitational form factors and double pattern correlation, because since we have these three particles in this individual three active quark, so we can also calculate the double pattern distributions. So this was the previous story. Now our ultimate goal is to solve like Light-Cone QCD Hamiltonian without any confinement. So for that, we need to include all this kind of QCD interactions, but this is like we are trying to do that. We're in the progress, but before that, going beyond this leading fork sector, in this picture we include like another fork sector where we have like one dynamical gluon. So this is the leading fork sector we solved before. Now we add another fork sector with one dynamical gluon, and for that purpose, we are fortunate to include like QCD interactions. The fundamental QCD interaction related to this fork sector, basically, this is like vertex interactions and instantaneous gluon interaction. So this is like QCD Light-Cone QCD interaction relevant to this fork sector, and we have also included confinement in the leading fork sector only. This confinement in the leading fork sector, basically our total Hamiltonian like P minus is equal to PQCD and PC. This confinement only in the leading fork sector. And we try to solve this equation again, this time independent Schrodinger equation. So we try to solve it, and we obtain this parameter by fitting this nucleon mass and the electromagnetic properties of the system. Okay, so once you solve this Light-Cone Hamiltonian equation, we obtain this wave function again, and we can further employ this wave function to investigate various nucleon properties for the quark case as well as the gluon case. Okay, so this is kind of the fork space decomposition. So for the leading to fork sector, we have, like as I mentioned, the kinetic energy term. We have confinement in the leading fork sector and the vertex interactions. For this type of Hamiltonian, after solving, we obtain that QQQ, the three particle fork sector contribute like 44%, and with gluon, one dynamical gluon, it's contribute like 56% from this. This is like probability of these two fork sector. So once we have this wave function, we can further employ to study the pattern. First is the pattern distribution functions. This unpressed pattern distribution function. So we can notice that this is the gluon distribution. So this is like before the red band basically without the dynamical gluon, but with this leading fork sector, and the blue is the with one dynamical gluon. We can see that after including the one dynamical gluon, our results approach this global fitting result. Although this quark distribution, U quark and up quark and down quark distributions, the unpressed distributions are more or less same with the previous result, but our gluon distribution improves. And I would like to mention one thing, that if we include the dynamical gluon in this picture, this was our previous initial scale, which we obtained by fitting the first moment of the pattern distribution function. So now our initial scale increase basically. So if we include more and more gluon in this picture, then our initial scale of the distribution or the model scale, that is also increased basically. Okay, so the next thing is that the helicity distribution. So here we have this like gluon in this picture, so we can calculate the gluon helicity distribution as well, and we compare how this blue band is basically our BLFQ result with one dynamical gluon. So we compare our result with this global fit jam and NNPDF 1.1. So we can see that there is a huge uncertainties from this global fitting result. So that's why I'm saying that gluon spin contribution is not well known yet, but our error band is quite small, which you obtain from the initial scale. There's uncertainty in the initial scale. So this is for gluon, this is for up quark and down quark, and here we can also see that after including the one dynamical gluon, our current result improves at the low X region as well as this high X region for this quark distribution. And with these are the C quarks. Since we don't have the C quark in this picture, initially we don't have C quark, but this C quark basically generated from this from the scale evolutions. And we can see this from this experiment itself that there is a huge error band, error uncertainties basically. And this even we cannot recognize the sign of these distributions. But we can see the C quark distribution itself is very small in our case because we don't have any C quarks initially in this picture. So the quark spin, if we from this polarized distribution, we can also calculate the quark spin. So we can see the U quark strongly dominate over the D quark distributions. And on the other hand, the gluon spin contribution is not small. It's like 26% basically. So it's a sizable portions of the proton spin. So if we compare our result with this Phoenix collaborations, they don't consider the whole range. They consider some certain range. They provide like 0.2, whereas our result is 0.13. Although the scale is little bit different. Scale is very different because our initial scale is just 0.23 GeV square. Okay. So the next thing is the helicity asymmetries. We know we have this helicity distribution, so we can also calculate these helicity asymmetries. Then we notice that this U quark distributions however, it deviates from this experimental data, but it approaches to 1 when X tends to 1. This is the prediction from this perturbative QCD calculations as well as the light from holographic prediction. On the other hand, we can see the D quark distributions remain negative. That is very interesting thing. So there is no experimental data at large X region, so we don't know what will happen in this region. But the holographic QCD, they predict that it should go to 1. It should approaches 1. But in our case, our result is consistent with the global fitting result. And this is for gluon distributions. This is also like more or less in agreement with the compass data, and it also approaches 1 when X tends to 1. Okay, so this was like what I was just talking about, this one-dimensional distributions. Now I'm going to talk about the like little bit more, like the gluon GPDs. The GPDs like it's like three-dimensional distributions. And GPDs are defined by these bilocal operators of this gluon operator. If we sandwich this operator between the initial and final state, we can define this for unpressed gluon. There are two kind of GPDs, H and E, and for the circularly polarized gluon, there is kind of two GPDs, because we consider like zeta equal to, skewness equal to 0. There is no momentum transfer in the longitudinal directions, so we cannot right now achieve this E tilde GPD, but we can calculate these HE and H tilde GPDs. So these are using our light from wave function, resulting light from wave function, we have calculated this quantity, and this look like this one. So we can see the gluon distribution is basically, we have this peak at small X region, which is expected. And if we increase our distribution, if we increase the momentum transfer in this process from the initials to final state, we can see the peak distribution shifted. The peak shifted to the right side of X and the higher values of X. This is like model independent features. So this distribution also obtained for like quark case as well as for any system. We can see this kind of distributions. And another thing is that using this GPD, we can also calculate the orbital angular momentum of the gluon that contributes to the proton spin. And we found that it's like total G is like 13.2 of the total angular momentum of the proton. So another interesting thing is that since we calculate the GPD, if we go to this, if we at the zeta skewness equal to 0 limit, if we take the Fourier transformation of the GPD with respect to the momentum transfer, that can provide some kind of distribution which have these probabilities interpretations. So using this impact parameter space GPDs, we can calculate this b squared, the square radius basically. So square radius, if we plot this quantity with respect to the longitudinal momentum fractions, we can see that when x0, the square radius is maximum, and if x goes to 1, so it's like the transverse separation, transverse distance of the parton is vanishing basically. So basically, if the parton carries the whole momentum, it's like a point-like particle. And if we compare our result, the gluon distributions to the quark radius, so we can find that small x region, the quark distribution is larger. Quark radius is larger than the gluon radius is larger than the quark radius in this small x region. And we can also calculate like the b square value after integrating over this x. So if we multiply this PDF and the b square values, we obtain like 0.47 Fermi square, where the experimental value is 0.43. Okay, so this is like kind of spin decompositions. As I mentioned, we need the gluon spin. So we know the spin decomposition with basically quark and gluon helicity. We can calculate from the helicity distribution. If we integrate out these helicity distributions, we obtain like a contribution for the quark spin and the gluon spin. And the total angular momentum is connected directly to the GPDs by G's sum rule. And the kinetic orbital angular momentum for the quark, we can also calculate the total angular momentum minus of spin part. That can be give the kinetic orbital angular momentum. The canonical orbital angular momentum can be obtained from these GTMDs, so which is like multi-dimensional distributions. So these are the relations. So if we calculate all this quantity, we can find that kinetic decomposition. So this is like quark spins strongly dominate over this gluon spins as well as the orbital angular momentum. Here we can see the gluon spin is like around 26%, 25%, and the gluon this orbital angular canonical orbital angular momentum is very small. Okay, so we have this gluon, so we can also calculate the gravitational form factor. Today morning there is a nice talk on this topic, but we have another talk actually. Siraj will talk about all this gravitational form factor in today afternoon. So gravitational form factor basically this expectation values of energy momentum tensor operator that can be parameterized in terms of 4 gravitational form factors. So that in our approach we can calculate A and B from the plus component of this energy momentum tensor, and C and C bar, these are 2 gravitational form factors that can be obtained from the transverse component of this energy momentum tensor. So I just present the initial some initial result of this A and B, and this is important because I just want to show this A and B. So they are basically related with this moment of the GPDs as well. So if we take the second moment of the GPDs, we obtain the gravitational form factor A and B. So they satisfy the sum rule. Basically, if we add the quark part and gluon part, the total momentum carried by quark and gluon, that should be 1. We obtain these things. This is the total part, and this is U quark, D quark, and the gluonic contributions. And also this the anomalous gravitational magnetic moment that should be vanished. This is Fock sector by Fock sector. So we achieve this sum rule as well. Okay, so the gluon. This is why is this? Okay, so this is gluonic TMD. So gluonic TMD can be obtained by this again. This if we have the gluon field and is sandwiched between the initial state and final state. So gluon TMDs basically there are 8 leading to gluon TMDs because they are parameter. These are the parameterizations depending on the polarizations of the target polarization and the gluon polarizations. We have different kind of TMDs. So these 2, the circle, F1 and G1, they have the direct connection with this PDF. Okay, I just want to show this result using again our gluonic wave function. We can calculate the gluonic TMD. This is for unpredicted distributions, and here is the other the slice for K-pop dependence and express dependence for particular values of fixed X and fixed K. So this is these are the 4 T event TMDs. There are 4 T event TMDs for gluon case, and our gluonic distribution, they also satisfy all these whatever this bounds. Positivity bounds, and also this Mulder's-Rogers relationship. This is the subset of this positivity bound. Okay, so I can skip these slides. This is like okay. The another thing is that we can we have we have the gluon in this picture. So there is opportunity. We have this opportunity to calculate the quark-gluon correlation, basically, which is very important to investigate the twist tree distributions. So this is the leading twist, the quark distribution. This is the leading to twist tree TMDs. If we compare that, they are more or less comparable, but they are connected through some genuine twist tree part. So this is very important quantity. If we don't have the gluon in this picture, you cannot calculate these things. Since we have the gluon in this picture, so we can calculate this part. So this is the genuine twist tree contributions to the total part, basically total twist tree PDF. Okay, so twist tree TMDs are important because of it is important to investigate the cross sections in the DIS process. So to investigate all the cross sections, you need like all the twist 2 and twist 3 TMDs basically to investigate all the spin asymmetries part. So all the red are for this twist 2, blue is for twist 3. So we have this twist 3 TMDs and we can calculate the twist 3 the cross section for the DIS process. I just want to just mention that. So this is the FLT. This is the one structure function, so which is connected with the twist 3 operator, twist 3 TMDs. The twist 3. This is the equation motion relations. And the GT can be connected with the G1T. This is the leading twist one. This is the genuine part. So we have all these ingredients to calculate this spin asymmetry. And important thing is that twist 3 contribution. There is a suppression part M by Q. If the energy scale is very low, so it's very high, then the asymmetry is very small basically. So only this EICC can there is opportunity to measure this quantity through EICC compared to this EIC, and this is the corresponding result for this asymmetry. This is for this EIC's case. EICC's case, so this is EIC's case. So we calculated this asymmetry and we found this all asymmetries are negative. Okay, I just want to mention this is very important things. This is ongoing project. Still now, I was just talking about the leading to Fock sector. So if we include the 5-particle Fock sector, then we can calculate the C-quark distributions. So in this case, there is a nice talk actually. Sichi will talk about all the detail about this 5-particle Fock sector, and he will also talk about another Fock sector basically once we include the 2 gluon. So in that case, our aim is to completely remove this confinement from this picture. We just include the kinetic energy part and whatever the relevant QCD interactions related to this Fock sector basically. So before we have these two contribution from this leading to Fock sector, but if we include this 5-particle Fock sector, we have this additional this QCD interaction in this picture. So again, we solve this eigenvalue equation and obtain this wave function, and this is the corresponding Fock space decomposition. So we noticed that previously it was like 44% from the leading Fock sector. Now it is like 46%, and the higher Fock sector is like 48% now. Previously it was like 56%. Although this 5-particle contribution, 5-particle Fock sector is not so big, but still it's very important to investigate the C-quark distribution. Okay, so this is. Okay, so this is like our initial distribution. So initial XPDF for the valence quark and gluon. This is the C-quark distributions of. We can see that D-bar is a little bit higher than this U-bar. This is the expected, right? So there is asymmetry between these light quark asymmetries in the proton. And this is the corresponding the helicity distributions for the quark case and the gluon case and D quark. And D quark is negative, which is expected, and this is also U quark is strongly dominate over this D quark, and this is the C quark. All the C quark helicity contribution is more or less same. Okay, so this again, since we have this C quark, then we can calculate the C quark GPDs. This is our preliminary result, where we found that the C quark completely dominates at this small x regions. This is for U quark, D quark. This is SS bar, and this is for E GPDs for U, D, and SS bar. So all these E GPDs are negative and A GPDs are positive. Okay, so this is the like final slide. I would say. So we can also calculate the C-quark TMDs, and we found that there is asymmetries, as I mentioned before. There is asymmetries. So if we plot like the unpriced distributions for D quark over this U quark distributions, so it's like a small x region is large and large x is small. So this is like expected behavior. There is also asymmetries in
in these helicity distributions. So the point is that we are trying to include more and more folk sector and try to get this information from the CQuark and gluons. So I'd like to conclude my talk now. So the basis light from quantization approach is like a non-perturbative approach. It can provide, it's based on the light from QCD Hamiltonian. So if we know this light from QCD Hamiltonian, we can diagonalize this Hamiltonian in terms of some basis, and then obtain this light from wave function, and then calculate the observable. So right now, we just discussed this leading to folk sector, what will be the gluonic contribution, how it look like the gluon distribution. And if we include more and more folk sector like CQuark distributions, we can also investigate if we have this three folk sector. So within these folk sectors, our result is quite good in agreement with some data or the global fitting result. And for this case, we have like initial result, we are trying to improve it. We have to fine tune our parameters, all stuff. And with this one dynamical gluon, we found that the spin contribution coming from the quark is like 70%, and gluon plays a very important role. They provide like 26% to the proton spin. And our next target is to include more and more gluon and other folk sector. Like we have like three gluon or four gluon interaction in these Hamiltonians. I would say this is like not the complete picture. We have to go along. So thank you for your attention.
Oh, I have to go there first.
All right, thank you for the nice talk with a lot of results. You quickly went through these gravitational form factors that I discussed this morning.
Right.
You didn't mention the C or the D. I mean, did you try it, and did you?
Yeah, we have this result. Siraj will talk about today afternoon about this other gravitational form factor.
And how does it compare with the lattice? Do you know?
It's good in agreement actually, but there is a problem with this scale, as I mentioned, as I discussed with you. This.
Okay.
So we have some approximate evolutions for this gravitational form factor because our initial scale is a little bit low right now. So we have to evolve to this 4 GeV² scale to compare with the lattice QCD result.
And now I maybe just to finish a question maybe to you, Jim. The issue is, so this looks good. We have known for a while, of course, that this expansion is quite large and it's challenging, and you took on this. My question to you is, in terms of predictions, how am I going to gauge myself when I should stop to make predictions? If you can give me a sense.
Oh, yeah, he wants to. It's a related question, but
That's an excellent question. He didn't have a chance to show the full picture of the plan for the future. We have something called what's called full BLFQ, and in full BLFQ, you only have the two regulators, Nmax and K. That sets the scale. Then if you set the scale and do the BLFQ, there's a cutoff in the Fock sectors defined by the scale. So you always solve the problem at a scale in this picture. So there's no end if you want higher and higher scales, but if you're only interested in 2 GeV², there will be a cutoff in the Fock sector in full BLFQ. But that's a point worthy of a lot of discussion.
Right.
yeah, the question I had was that in some point, including this higher Fock state, you say that you neglect the confinement
Right.
part.
Right.
So are your degree of freedom that you are dealing with, is that if you don't include the confinement, then those are the free quark and gluons?
No. We have this QCD interactions. Still, we have this.
So what is this confinement is not there?
Yeah, we want to solve like from the first principle calculations. Still date, we just use this kinetic energy term. We have this confining potential. We are trying to include more and more QCD interactions. So our approach is now we completely ignore this because this is like from phenomenology. We adopted from some other approach, but we are trying to
Yeah,
solve.
but I mean, the moment that you drop the confinement,
Yeah.
how can you say it's QCD?
Yeah, because we want to try to predict some whatever this available distributions previously.
Yeah, but I mean, those are, if you don't have a confinement,
yeah,
then they are really like a free quarks or gluons you can have, right?
but they are not free. They have some interaction, right?
Yeah, but they can be unshared or they can be measured, you know, isolated quarks and gluons.
But they are
can
within
be,
they are within this proton.
yeah, but so that's the question. I mean, if you drop the confinement,
Right.
and then do the calculation, that will be, you know, not really the, you know, QCD quarks and gluons.
But from the light front QCD Hamiltonian, it's okay. I can go back. Just yeah, this is the picture, right? We want to solve this.
Sure, these are the perturbative, you know, SU3 color
right
things. But you have also the global SU3 color.
right.
Everywhere it has to be color singlet, and then you shouldn't have an isolated, you know, free quarks or gluons.
In BLFQ, with these choices, you have in an ultraviolet regulator. With those regulators and the choice of the modes, there are no free quarks.
Yeah, they are not
That's the point.
right.
But as you evolve the scale, the potential for free quarks would be there. We don't know yet whether they will actually emerge as you go up in the UV and down in the IR scales. But they're not free at the present time.
Yeah, that is our target, to see whether we can achieve the proton structure without any confinement with this only just QCD interaction.
Interesting to see.
Yeah.
Compare if you include the confinement.
I have a related question. When you compute these quark distributions, at which scale are they computed?
Okay. I can show you this result actually. Yeah, so this our initial scale. We obtain this initial scale basically by fitting this first moment, the first moment of the PDF. When we evolve our PDF to some higher scale, let's say 10 GB square, and compare our result with this global fitting result. So this result is at 10 GB square, but our initial scale is like 0.195 or 0.23.
Nice talk from yesterday's talks and also yours. There's the separation of transverse, like the basis versus longitudinal. Is that clear? That's always a good idea. And at some point, is there cross-talking between the transverse dynamics separated from longitudinal dynamics everywhere?
Yeah, that was like with this effective Hamiltonian. Once we include like the confining potential. So confining potential, the transverse confining potential, basically we use like harmonic oscillator. This is just because we use harmonic oscillator basis function. So on the other hand, we need in the longitudinal direction, we also need confinement. So this is, of course, this is completely separable, but we need this confinement in the longitudinal direction.
If I see, like, for example, people show diagrams from JLab or other places where there's a clear, if you wish, growing an impact parameter as you go to smaller x, can you accommodate that sort of a thing?
Right
if
now,
you assume that there's separation.
Yeah, the problem is that in our current basis, we cannot achieve. Okay, so here you see for this, let's say I can say these things. So this is our basis size, like n max equal to 10 and n max equal to 9 and k equal to 16. Basically, that we cannot achieve low x region. We'll achieve some, let's say 0.93 or maybe 0.03, the beginning point. So we have to do these things if we increase more and more, increase the basis size in the longitudinal directions. Right now, we have some truncation in the longitudinal directions, which is not enough to achieve the low x region.
Any three-dimensional function would be a power. Doesn't mean that the dynamics are defined. No.
This is right.
Okay, so thank you once more.
Thank you.
And I'll have the last talk of the morning session.
Thank you. Se apertar uma vez,
Esse aqui, próximo slide, e de baixo para trás.
o laser aqui demora.
Laser.
Okay. Yeah. So thank you very much for having me here. Thank you for the support from the organizers. I'm going to talk a little bit about correlations among the partons, especially valence and C partons. And we are talking about double parton scattering. That's a little bit, it has been touched already in some of the presentations I saw, but here we will talk almost all about it. So we'll focus on double parton scattering. That means we have two hard scatterings, A and B. We can produce, like, for instance, J-psi here, and we can produce dijet here, or some other combination. This would be the final state. But this happens, the hard scattering, the two hard scatterings happen independently, because you have one parton from one proton colliding with the parton from the other proton to make up for the A final state, and the B final state will be another pair of partons. And this, of course, has been measured, and we have an idea of what would be the most general way to calculate this double parton cross section. Then we would need this matrix element for A and B, and also we need parton distributions that depend on x1 from one parton, x2 from the other parton, and there is some transverse distance between the two points in transverse space that where the hard scattering is happening. Okay. Well, this is very, very good to have these expressions, but actually we don't know these functions precisely. This is our topic of interest. So we want to understand not only how the partons are inside the proton in the longitudinal space, but also in the transverse space. And then, well, we can put a very simple model with no correlation, basically no correlation except for large X. You cannot get more energy from the partons than you have in the proton. So you can do this kind of model and assume maybe this does not depend on the parton flavor or parton kind, or it doesn't depend on X. So you have a factorized ansatz, okay? And then if you do that, basically, if you do that, you get a much more simpler expression for the double parton scattering cross-section. You have the one scattering cross-section and the other one scattering cross-section for A and B. By dimensions, you already know that you should divide by something that has the dimensions of a cross-section. And then this is what we call the effective cross-section. If it's large, we get less double parton scattering, okay? If it's small, we get more double parton scattering. And then you know how to calculate these two guys here in the numerator. The only thing you have to do is to measure the denominator, and then you all set up, right? If you do a simple model,
a toy model, let's say this is a hard sphere. The proton is a hard sphere without correlations between the partons. You can do some calculations, and then you can get the effective cross-section of 38 millibarns, okay? And you see if the proton grows, if the radius grows, you get a larger effective cross-section and then less DPS, less double particle scattering. And we go to the measurements. Many people have measured that. You got here the experiments, and you see that they measure with J-psi, with Z boson, W boson, gamma photon, right? 4 jets, everything. So you can combine many final states, A and B. And then you get the measurements of the effective cross-sections, and you see that 38, maybe it's a little too big, okay? So the effective cross-section is smaller than 38. So this means we're getting more DPS. But also there is an important thing here is that everybody's claiming that they are measuring the same effective cross-section, or maybe I'm claiming for them, right? But they are measuring the same effective cross-section using different final states. And they're getting different results. You can see here that the results are very different if you consider the error bars. The error bars are small. And you see that J-psi, for instance, when you add J-psi, you get a small effective cross-section. When you have jets, maybe lower energy as well. There are many factors you can think on how to organize this, but you see that you have many values. So we would like to have a better understanding than this simple model here, that we just get just one number here. Maybe there is more than one number. The problem is this number depends on the initial state, and what we are seeing is a difference because of the final state. So how do you solve that? Well, let's propose maybe that there is a dependence on the parton kind. By parton kind, I mean if it's C quark, or of course C gluon, or valence quark. So maybe the valence ones are less correlated than the C partons, okay? And then different final states will draw more contributions from valence partons or C quarks. And then you have the difference between actually it's not a difference in the final state, but it's because the initial state that contributes to the final state relies more on valence or C partons. So we did that. We have to do, we still use a factorized ansatz, but we put that this contribution here that will tell us the distance in the transverse plane will depend either if you have C or valence quark. That's what I mean by S and V. And then you can redo the math and you get a little expression here for the double particle scattering. That's the sum of all of the contributions, each one with an effective cross-section. Then in the next slide, how do we get the effective cross-section from this theory? Well, we'll have to combine the single particle scattering cross-sections for producing A and B. In the numerator, they are combined very easily. And the denominator, they are weighted by the effective cross-section. And then we go on Pythia. We use just vanilla Pythia because we don't want to tune Pythia to one experiment or other. We want to use something that can be used abroad of all courses, of all types of experiments. And then we calculate this cross-section by this effective cross-section in the theory. So if it is smaller, it will mean that we have more correlations between those kinds of partons. Right, so we have this free parameters that are the effective cross sections involving different kind of partons. So we have maybe all the four partons are from the C, or maybe they are from the valence, but we also have other combinations. Actually, these four here, these last four, unfortunately, the experiments are not sensitive to it. You can put any number there, it will not change the results. So the main contributions to all those final states that were measured actually involve 4 C partons or 3 C partons and 1 valence quark. And then we do minimization, etc. Okay, and then we got to these results. If you do just one effective cross section, okay, we get this value that's approximately 10, right? But it's not very good. We can exclude it because of the error bars. We can exclude it with 3.8 sigma. It's not 5 sigma, but it's already very good exclusion, right? And then in our study, in our idea, let's fit these 2 parameters. And then we have these values, and we see that when we involve 1 valence quark, we have less correlation. So less DPS, larger effective cross-section, and the results very significant. Okay, maybe plus minus 15 is not, it's a large error bar, but still this is outside this error bar, so we think that's good. And we got chi-squared of 1.7. Not saying it's going to be very good, but it's not bad. Okay, 1.7. We already think it's a good chi-squared. And then we can do the same plot. And then we have the experimental measurements in blue and our fit in red. We see that we get most of them correctly. So this is a good sign that we are walk towards a better understanding of what's happening. And we published, well, I mean, it's accepted for publication, J-HAP, this work. And now we go back and think, well, maybe a little bit more bother because it's 1.7. Perfect chi-squared is 1, right? Maybe we should get it smaller. What else can we do? Maybe introduce some X dependence, and then we have dependence. The impact parameter dependence, it correlates also with X dependence. This has been done in other processes, like J-psi, for instance. In J-psi, you get the slope to depend on X. So maybe this will be important for us as well. And we are working on that. We try some different expressions for this dependence on X and how we are going to combine to produce this function that show us the correlations between the partons. So to summarize, I would like to say that we studied the transverse distribution of different parton kinds. And we found out that maybe C partons are more correlated than valency pairs. That's what we saw. The fit's not bad. We're happy with it, although we want to improve the description of the PS, maybe including also X dependence. And that's it. Thank you very much.
Okay, good questions.
Manuel, thank you for the talk. I'm just curious, you mentioned correlations. I had in my mind the correlations among the quarks within the nucleus. You have not touched that. I was thinking, because you say correlation between the quarks in different nucleus.
No, in the same nucleus.
In the same, I couldn't get that.
Yes, let's.
If you could give another explanation.
Yes, fine. So I guess, well, here or here. So have this function here. It depends on R, and R will be the distance between these two guys here, but it will be also going to be the distance between these two guys. So we are correlating the guys from the same side here. So this is x1 and x2 are two partons coming from one of the protons, and the distance in the transverse plane will be r.
Later on, you factorize that.
Yeah, factorize everything. Right. Okay. So yeah, actually, if you say that this works, you factorize everything. And you're saying there is no correlations, it doesn't depend on the final state, everything, right? And this is used, this is not something that's too naive. This is used to study this double particle scattering. What we are going to do, what we're proposing to do, let's maybe do one step better. We're not solving the whole problem, because there are many uncertainties in this function. Maybe we're not claiming we can understand everything about it, but maybe we can understand that there is an important difference between valence and C particles.
Do you have an idea of on the nature of the correlation? You just see that there is a correlation, but color, spin, space.
Yes. Well, we actually had some models when we started the project and toyed with them, but maybe we try to do something that, well, no model, let's just see what data is telling us. But we have some ideas. Maybe valence quarks are more apart, and then you have strings of gluons. This is one of possible model. So the gluons will be more correlated, and they are from the sea.
Thanks. The question, but the comment, but you may be familiar with like saturation, people doing this, let's say, transverse profile of a proton, and they go beyond it and try to do like fluctuations, and they call like hotspots and things. I wonder if you could try those and how that would affect your results.
Yeah.
Does it make sense or not?
This is one of the models that I was mentioning as well. That will be hotspots. The problem is if you evolve the hotspots, you get a lot of hotspots, and then you lose correlations, right? And we wanted to show the correlations. So maybe I'm more inclined to a kind of wounded quark model, right?
Okay. Now, about that product, Fix1, Fj(x2). So if you have a model like we have seen from Chanda or other 3 quark models, you have this correlation. I mean, because your wave function depends on x1 and x2. So you could even get, not in a complete, I mean, if you use back model, then factorize, but in this kind of 3-body wave functions that we have seen, the valence part, you could get that. To see.
So maybe that's an invitation for them to calculate and compare with our results, right? Yeah, that would be nice.
Okay, I see no other question. Thank you again. And with that, we go for lunch. Do you have an announcement?
I need only those ones that are not going to the banquet. Please tell the secretary, because I need to have the exact number. Thank you very much. Please, and don't forget the talks of the afternoon.
Ahí. Hola. No. Oh. Oh, Marcela.
Marcela.
Sí, mucho gusto. Sí, de Uruguay. Ah, muy buena charla. Sí. Después me quedé con alguna pregunta que gustaría de hacer. Sí. A ver. Ah, más arriba.
¿Tú conoces a Mathieu Tissier?
Sí, fue mi orientador de doctorado.
¿Qué? Fue tu
Sí. ¿Por qué?
era estudiante.
Ah, ¿esto está funcionando?
Creo que sí.
Sí.
Y como sé que iba a Uruguay, no sé si
Claro.
todavía va.
Sí, sigue con la colaboración.
Continúa.
Tiene una esposa uruguaya ahora.
Ah, ok.
Bueno.
Estudiante mío.
Ajá.
Y ahora estoy hasta en París.
Sí.
Y a veces no sé.
Porque yo fui ahí, a Jussieu, sí, en Jussieu. Ah. Y este trabajo que voy a presentar también.
También.
Está muy clarito.
Pues tenemos primos.
Ah.
Hello, welcome everyone. This afternoon, start the session with Marcela Pérez from Uruguay. She work about cation-pion decay constant with massive gluons. Please, Marcela, go start.
you.
Thank you.
Okay. As you want.
Não tá na hora.
Okay.
Sorry, my clock is wrong. 2 minutes, I think. Well, the first
Rewind.
because this morning is too late and then I started a little bit early, you know. Okay, 2 minutes, okay. Yeah, 1 minute now. Sorry, I think she's sorry. My
Sí.
clock is wrong.
Urco también y Julián. ¿Fue estudiante de doctorado de usted? No.
Wrong.
Sí.
Okay. Now can start again with Marcela, please. Sorry about.
Okay, so first, I want to thank the organizers for giving me the opportunity to give this talk. I'm going to present a work that is in collaboration with Nahuel Barrios, Urco Reynosa, Julian Sarraud, Mathieu Tissier, and Nicolas Chevor. And it's about computing the pion decay constant in a model that is called Curci-Ferrari model that use a mass for the gluons. Okay, so the outline of the talk is that first I'm going to present what is the pion decay constant, and then the ingredients that I'm going to use to compute it, that in particular are the model that is called Curci-Ferrari model, that is a model that includes a gluon mass term, and then I'm going to try to show you that we have two small parameters, even in the infrared regime. So this will allow us to organize the diagrams that we need in a controlled way. So with those ingredients, we are going to come back to the pion decay constant and compute it, in particular in the chiral limit. And then I'm going to show you some numerical solutions and, of course, the conclusions. Okay, so the pion decay constant is related to the decay of the pion into leptons and neutrinos, but the strong contribution, the strong interaction for it is given by the pion, this correlator, that is the coupling between the pion and the axial current. So in fact, we want to compute this kind of correlators. And of course, if we want to be exact, we need to include here a lot of diagrams, infinite diagrams. So we can do that. So we ask ourselves which diagrams we must or we want to include there in this approximation that I'm going to present. So I'm going to show you that even in the infrared, there are some small parameters, and having small parameters is good because this allows us to organize the diagrams in a controlled way. And I said, even in the infrared, because as you all know, in the ultraviolet regime, the coupling constant decreases. So it's a good regime to apply perturbation theory. However, if we compute the coupling constant using one loop or two loop corrections, using the standard Faddeev-Popov-Lagrangian as we do for the ultraviolet regime, this coupling is going to present a Landau pole, so it diverges in the infrared. So in order to study the infrared regime, we need to do some other alternatives, for example, Dyson-Schwinger equations, or functional renormalization group equations, or some Hamiltonian approaches. And of course, we have lattice simulations to study this regime. And lattice simulations, in fact, found that the coupling constant does not diverge, so it doesn't have a Landau pole. This is the coupling constant obtained from the ghost gluon vertex. And in fact, the expansion parameter, that is alpha over 4 pi times n, is actually not so large. So we think that, or we wonder why does perturbation theory doesn't work at all. So at least we think it shouldn't be so terrible as with Faddeev-Popov-Lagrangian. And maybe one explanation is because Faddeev-Popov procedure, in order to fix the gauge, is not completely justified in the infrared because of the Gribov copies. So actually, we don't know exactly what is the way that we need to fix the gauge in the infrared regime. And another observation from lattice simulations is that the gluon propagator here saturates in the infrared, so it behaves more like a massive particle than a massless propagator. So our model consists on taking the Curci-Ferrari model, that is a model that includes a gluon mass term. This is the expression in Landau gauge. So in Landau gauge, this model is just taking the Faddeev-Popov-Lagrangian and adding just a gluon mass term. So in this situation, we already fixed the gauge. Yes, so this is a modification for the Faddeev-Popov-Lagrangian. And this kind of Lagrangian have been proved to be renormalizable. And in fact, they allow an renormalization scheme that is infrared safe. So that means that we can find a normalization scheme for this Lagrangian that where the running of the coupling constant does not diverge, does not present a Landau pole, as what we want from lattice simulations. So the first thing that we have done with this Lagrangian is try to compute some correlation functions, first at one loop. So we have include the one loop corrections. This is the gluon propagator, and this is the ghost tracing function. Of course, the tree level here is obtained from that Lagrangian, the Curci-Ferrari Lagrangian. So the propagator has a massive mass for the gluons. So we have computed the one loop results and also the two loop, and we can see that the corrections between going from one loop to two loop are small, so that's good in perturbation theory, and also they go in the good direction. So that's what we want from perturbation theory. We also compute the one loop and two loop corrections for the ghost gluon vertex and also for the tree gluon vertex. And we also obtain very good results in the case of the correlation functions that involves ghosts and gluons. And this is the comparison with the coupling constant. Those are the dots are lattice data, and then the dashed line is the one loop calculation, and the other one is the two loop calculation for the coupling. So we have seen that correlation functions in the Gauss-Gluon sector, that means the correlation functions that involve fields that are Gauss or gluons, can be well reproduced using a perturbative description in this model that includes mass term for the gluons. However, I don't have the plot here, but the situation doesn't work as well for the quark sector. So if we compute correlation function that includes quarks, they are not so well reproduced in the case, especially when we approach the chiral limit. And we can understand this because the quark-gluon coupling constant, that means that is the coupling constant defined through the quark-gluon vertex, is related to the Gauss-Gluon coupling constant, so the coupling constant defined through the Gauss-Gluon vertex, by a factor λ1 that can be measured on the lattice. And this is, okay, the value of this function depends on the cinematical configuration where the quark-gluon vertex is computed. But in the infrared, actually it has the value 2 or 3. So the expansion parameter that comes with chi squared is around 4 or 9, between 4 and 9 times larger in the quark-gluon sector than in the Gauss-Gluon sector. So in this model, what we are going to think is that we are going to treat differently the coupling constant defined through the quark-gluon vertex and the coupling constant that is defined from the Gauss-Gluon vertex, and actually that is going to be treated on the same footing and for the gluon self-interactions. This means, of course, the coupling constant is related to the same Baire value, because in the Lagrangian we only have one coupling constant, but we are going to renormalize differently the coupling constant obtained from the quark-gluon vertex and the one obtained from the Gauss-Gluon vertex. And as we have seen, we are going to consider the coupling constant in the Gauss-Gluon sector as a small parameter, because when we compute these correlation functions, perturbation theory works well in this Cauchy-Ferrari model. So our first small parameter is the coupling constant obtained from the Gauss-Gluon sector, but also we are going, this is more for practical reasons, to consider the large NC limit. NC is the number of colors. So we are going to, we are going to think in the 't Hooft limit. So the gluon in the large NC limit can be thought as the interchange of color. The coupling constant is going to scale as 1 over the square root of the number of colors. And there we can study what is the behavior of the diagrams in terms of the color. And we can see, for example, that there are some diagrams that are of the same order in the loop expansion, but they behave differently in the large NC limit. For example, this one is of order 1, but this other one that is not a non-planar diagram is suppressed in the large NC limit. And also, this diagram, that is a 2-loop diagram, is the same of the same order in the number of color as this 1-loop diagram. So now with these two small parameters that are the coupling constant in the Gauss-Gluon sector, that is the red one, and also 1 over the number of colors, we are going to do propose an order for the diagrams, and the order is the expansion is the following. So if we want to compute the L order in this expansion, we have to take into account all standard L-loop diagrams, count the powers in the coupling constant, in the red coupling constant of those diagrams, and also study the large NC behavior. And also add higher loop diagrams that behaves in the same way in the coupling constant and in the number of colors. So to have an idea, if I want to compute the one loop correction in this approximation, I have to pay attention to the one loop diagram and see that it doesn't have any Gauss-Gluon coupling constant. It doesn't have any red coupling constant, and it behaves is of order 1 in the Larsen-C limit. So now we are going to look for higher loop diagrams that behaves in the same way. So we can neglect all the diagrams that have a red coupling constant, and also the ones that are suppressed in the Larsen-C limit. So the only diagrams that are going to remain are the ones that are the rainbow diagrams. So for the quark propagator, in the first order in this function, we obtain all rainbow corrections, and of course it can be resummed in what is called the rainbow approximation. That is the well-known approximation for the quark propagator, and it has been exhaustively studied. We know that for large coupling, this equation can reproduce, for example, the chiral symmetry breaking. If we implement this expansion, also a first order in this approximation, for example, for the meson propagator, we have to include all the diagrams that are in this way. So we can include all the ladder gluon here. And also the bold quark represents the rainbow quark. Yes, so every time that the quarks appear, it appears in the rainbow form. Okay, so now that I have presented the way that we are going to order these diagrams, we can answer the question of which diagrams we are going to put in that correlator. So at first order, this correlator can be represented as this bold line are the rainbow propagator, and in the vertex, we are going to have all the ladder contributions. So we do this because in this approximation, all those diagrams are of the same order as the one loop diagram. So here we have the correlator, and when the propagator appears, we have to include the rainbow form, and when the vertex appears, we have to include the ladder approximation. Okay, so now we can study, for example, the pion quark vertex. So we have the ladder approximation, and we need to solve this Bettel-Salpeter equation in the ladder approximation. So here is, as we want to compute near the chiral limit, it's better to express the vertex in terms of the regular functions. So we are going just to rewrite the vertex in that way. And also, if we study the symmetries of the pion quark vertex, we are going to have different tensorial structures. For example, we have a pseudoscalar part, a tensorial one, and the axial part that is antisymmetric. So the Bettel-Salpeter equation is going to give us an equation for all these three quantities. Okay, so we are going to study the chiral limit. So what we are going to do now is to expand our expressions around p² equals 0 up to the linear order. So if we do that, okay, we are going to introduce another function that is gamma b. And we can see that the equation for the pseudoscalar part actually decouples from the other ones, and in fact has the form m over z, where m and z are the scalar functions for the quark propagator in the rainbow approximation. We can also check that this is also a consequence of the Ward identity, because if we start for this Lagrangian and we compute the Ward identities, we are going to relate the pion propagator with this axial pion correlator, and this is going to give us the same result for gamma p. Okay, so we have here the Bethe-Salpeter equation in the rainbow ladder approximation with a kernel that is obtained from the diagrams. So we know the form of this kernel. We need to renormalize the variables, so these are details. We also need to use a normalization group method in order to relate the functions that are renormalized at different scales. And once we have done all that, we have the final expression for our vertex that is also coupled with the running of the quark mass, the dressing of the quark propagator, the coupling constant, and also the gluon mass. So if we put, okay, this is just to show you the equations. So here we have this lambda is related with the coupling constant, and we also have the gluon mass term here in the middle of the equations. And all this equation is coupled also with the solution for the rainbow equation for the quark propagator, the mass and Z. Okay, so with those expressions, now that we have the propagator, that it was here, and also we have the vertex, we can put all the ingredients together, take the limit, the chiral limit, and obtain the expression for the chiral pion decay constant. And in fact, we obtain that expression in terms of an integral, a one-dimensional integral that, okay, the ingredients there are of course, the quark propagator and also the vertex. This equation, if we just take the first line, corresponds to the Pagel-Stockard approximation. That is the situation when we only consider the pseudoscalar part. But if we want to consider also the axial and tensorial part, we have to include the second line. Okay, so now we want to see how it works numerically. So if it's going to reproduce well the pion decay constant. So first we need to compute the rainbow equation for the propagator. That is, of course, is coupled to the running of the coupling constant and also the running of the gluon mass. Those running are computed to also at one loop in this approximation. So every time that the quark propagator appears, it appears in the rainbow form. So we have a system of those equation coupled, and we have to solve it. And once we solve it, we can obtain, we will reproduce the chiral symmetry breaking. This is comparing with the lattice data, the most next to the chiral limit data that we have. And this is the dressing of the quark propagator that actually is this function doesn't work too well in this approximation. But okay, at least it goes around 1, so it doesn't present a lot of changes. Okay, so now that we have compute and solve the rainbow approximation using all the runnings that we need to use, we can go and put the solution in the ladder expression for the Bethe-Salpeter equation and also solve that equation. And when we do that, we can obtain information for the tensorial part of the vertex. So we have gamma T, gamma A, gamma B. So that means that we can solve the ladder approximation for the Bethe-Salpeter equation. So now we have all the ingredients. We have the propagator, the vertex, and we can put it in our expression for the pion decay constant. And what we plot here is how the pion decay constant, using this expression, of course, is evolving while the iterations for the Bethe-Salpeter equation are done. So the first point corresponds to the situation where only the pseudoscalar part is taken into account. So this corresponds to Pagel-Stockard's formula. But then the iterations start to evolve, and very fast they converge to a certain value. Of course, here I need to say what are the free parameters and how I'm going to fix them. The free parameters are going to be the coupling, the initial condition of the running coupling constant, and also the initial condition of the running of the gluon mass. So we have studied the result for the pion decay constant, but in terms of the initial condition of the gluon mass and also the coupling constant. And we have observed that if we compute, okay, the pion decay constant, this is the blue region, and if we compare that region with the parameters that will reproduce the quark propagator, in comparing with the lattice data, that is the light blue region. So what we observe here is that in a way we can compare, we can reproduce the quark propagator. We are going with this expression to have a good result for the chiral pion decay constant. Okay, so to conclude, I'm going to summarize. So we have checked that with Curci-Ferrari, when we do perturbation theory, we can well reproduce the Gauss-Gluon sector, so correlation functions in the Gauss-Gluon sector. However, this is not the case for the quark sector. So that's make us think that we need to treat them differently in the infrared, of course. So they are going to be renormalized differently. The coupling constant obtained from the gluon Gauss vertex with respect to the coupling constant obtained from the quark gluon vertex. So in our case, the coupling constant in the Gauss-Gluon sector is going to be treated as a small parameter. And also, we are going to treat a small parameter 1/nc. In this way, if we do this, the approximation scheme will take us to the rainbow approximation for the quark propagator and also to the rainbow ladder expression for the Bettel-Salpeter equation for the pion quark vertex. And also, if we work with those equations using this gluon mass term, we can obtain an expression that is exact in this approximation for the chiral limit for the pion decay constant. And we have checked numerically that the region of parameters that give a good pion decay constant is the same as the parameters that are going to give a well-fitting for the quark propagator. Okay, that's it. Thank you.
Yeah, thanks for Marcela. Nice talk and respect the time.
Yeah, thank you. It's very interesting. For chiral symmetry, I think usually in QCD people talk about the Kellman-Oaks-Renner relations.
Yes.
Where the quark mass goes to 0, the pion mass goes to 0.
Yes, and you have
different
the
powers and so on. Have you checked that?
Yes, yes. Actually, in this using this Lagrangian, if we implement the Ward identities, we also obtain the same Renner-Oaks Gell-Mann equation, and this is going to relate the masses and F pi also with the condensate.
Right.
So we have computed also the condensate in terms of the. I didn't have the time to put in here, but we have checked that, and we also obtained good result for the condensate.
Yeah. So one thing I wonder is that because of I think your gauge choice, you are introducing this quark mass from the beginning.
Yes, the gluon mass.
But the well-known, it's one of our NC stuff. In fact, I was wondering your, sort of this parameter regions didn't cover M all the way goes to 0, but it has to, have some finite mass. I couldn't, in some sense, I couldn't really understand that. Usually, we think that the gluon mass is 0 and so on because of gauge symmetry and so on. But of course, this is a particular gauge, but
Yes,
Yeah,
what
I was
we
wondering
see,
about.
at least in this calculation, if I try to go to a zero mass region, the program start to giving the nonsense things and explodes. So it's like a region that we think that with this we cannot reach. Yes.
Okay.
Actually, I think it's because this mass acts as a regulator in the infrared. So for all the expression that we are computing, it's like okay, we need it just to be infrared safe.
It might be interesting to look at, 1/NC corrections as well.
Okay, yes. Okay.
So come on.
You said you are going to compute the spectrum of the mesons, the pion,
Yes.
but the interaction is entirely defined from what you have, or you have to add something. I mean, the quark anti-quark is fully determined.
Yes, but in this approximation, so we are going to compute it in this rainbow ladder approximation, but with the addition of this gluon mass.
So
Yes.
what will be the interaction between the two quarks? You have a confinement term and one gluon exchange, and one massive gluon exchange,
Yes.
and a confinement term.
Okay, we haven't arrived to that problem yet, but I think we are going to need to think about the confinement problem there. Yes.
Hi, thank you, Marcela, for the talk. Maybe you can show, can you show the running of the mass again? Because you fix the initial condition at some energy scale. At what energy scale do you fix the initial condition of the flow?
You say in this case?
No, the gluon mass.
For the gluon mass, okay. Sorry. So I don't, all the plots are not for the running of the gluon mass. Maybe I should.
The running coupling, maybe it will be.
No, what I have in terms of those are these. So just the initial condition at, I think it's at 1 GeV, if I'm not wrong.
At
in
one
terms of the
GeV.
Capricorn. Yes.
Because your running is such that if you go to larger energies, the mass will be smaller, right? It will run to smaller values.
Yes, yes, because the mass also has a running. Yes.
Exactly. So
yes, maybe a good idea is I should include a plot for the running of the gluon mass.
because for very high energies, the mass is going smaller and smaller, and this correction won't be
yes,
relevant.
the ultraviolet goes to zero.
Yes.
Please, Helen.
Marcela, one question.
Yes.
Your coupling for the quark gluon, where you renormalizing? What point? Because, for example, in this plot, you don't have any notion about what is the point that you are renormalized for those values that you have.
Yes, actually, in the work we have the normalization point was at 10 GeV, and that was a good thing for us because at 10 GeV we can consider that we are more or less in the perturbative regime, so we can relate the quark gluon coupling with the ghost gluon coupling. So in fact, we have only one parameter that is the initial condition of the coupling, and then they run differently to the infrared. So yeah, okay. Then we relate the 10 GeV condition to what are the equivalent to at 1 GeV. Okay, the program is done fixing at 10 GeV, but then we try to see how it works in terms of the mass and the coupling constant at 1 GeV.
Okay, I can say thanks again.
No,
Marcela, sorry, I can't this question. Thanks a lot. Now, Wayne De Paula from ITA, colleague from Brazil, please. pion transverse momentum distribution in Minkowski space.
Okay, thank you, Pacheco. Good afternoon. So I will continue the presentation of Marcela, very nice presentation. Continue talking about the pion. So here in this talk, I will show a model to calculate some pion observables, in particular the TMDs in Minkowski space. Those are the collaborators of this work. Abigail Castro, Diana Duarte, Giovanni Salmé, Tobias Frederico. Okay, so this is the summary of my presentation. This model is based on solving the Bessel-Peter equation. So we treat the pion as the bound state of quark and antiquark. In particular, the calculation is done in Minkowski space, and we calculate some observables. And I will also discuss some future applications for the dressed propagators. Okay. O pointer é onde? Aqui? Não. Quer dizer... Não tá. É? Ah, tá ok, beleza. Obrigado. Okay. So, this is an overview. We all know that the pion plays a fundamental role in QCD due to its Goldstone boson nature, because it's associated with the dynamical generation of the mass, and also this is the simplest hadronic bound state. So one of the challenges is how to extract from Euclidean calculations like lattice QCD some Minkowskian physical quantities like PDFs and TMDs. So, and we also know that we have the momentum distributions are a target of interest, intense investigation, and that the future EIC will certainly bring a detailed 3D image of the hadronic structure. So what is our goal? Is to calculate pion observables in Minkowski space. And the approach that we are pursuing is based on solving the Bessel-Peter equation in Minkowski space using the Nakanishi integral representation. So the using of this integral representation is the basis of our approach, and this is the reason that how we can manage solving the equations in Minkowski space. So this is the very important point that our model. Okay, so here is our Bessel-Peter equation that we want to solve. In the left, we have the Bessel-Peter amplitudes, and in this model, I'm presenting Baire propagators for quarks and gluons. We have ladder approximation, considering also massive gluons, and we consider also an extended quark-gluon vertex. In this quark-gluon vertex, we consider only one of the longitudinal components that it's proportional to gamma mi. And the scale parameter that enter in this quark-gluon vertex, we took from some analysis that we did combining lattice simulations, quark gap equation, and Ranoff-Taylor identity that we did with Orlando. Okay, so this is the model. It's a simple model, but we are solving a non-perturbative equation that is the Bessel-Peter equation. So in this way, we believe that we can give some hints of these observables. So we take our Bessel-Peter amplitude and we expand on a basis of Dirac structure. And once we expand on this basis, appear some scalar functions. And these scalar functions, we use the Nakanishi integral representation. So this momentum K and P P is the total momentum of the bound state, and K is the relative momentum of the constituents. All the analytical structure is explicitly given in this denominator. So this is the reason that we can solve the four-dimensional loop integration in Minkowski space, because we give the analytical structure. So this is the, and using this prescription, we can write the system of coupled integral equations that's given now in terms of this unknown function that are the Nakanishi weight functions. So, so this unknown function depends only on these variables, gamma prime and z prime, that are integrable. And we can perform a projection of this Betz-Opiter amplitude on the light front plane. So we use now light front variables, x plus, x minus, and x perp, and we project this on this hyperplane. And this projection is done by integrating over the k minus variable. So with this projection, we can eliminate the relative light front time between the two constituents. And finally, the projection of these scalar functions, we call this the light front projected amplitude, this psi-s. So this is can do it analytically. And in the end, we have a coupled integral equation system in terms of these Nakanishi wave functions. So this is now after all these manipulations, we have a coupled integral equation system that we can manage numerically. So this is a proposal of Carbonell-Karmanov that we follow in our prescriptions. And we can, of course, this kernel has some singularities, but we can treat it analytically before making the numerical calculations. And in the numerical calculation, we discretize it using polynomials base of Laguerre and Gegenbauer. So in the end, we have a generalized problem, a generalized eigenvalue problem with a non-symmetric matrix and a symmetric one. So we solve it numerically, and we can obtain these Nakanishi wave functions. Once we have these Nakanishi wave functions, of course, we can come back and obtain those scalar functions, and then we have the full Betz-Opiter amplitudes. So now using these Betz-Opiter amplitudes, we can calculate observables. So this is the idea. And one thing that we can calculate is the light front valence amplitudes that we can write in terms of these Betz-Opiter amplitudes that we can now. And these in particular, we can decompose into spin configurations. One is the anti-aligned spins of the constituents, and the other is the aligned one. So all of the observables we can write in terms of these two configurations. And those are our quantitative results. So this M is our quark mass, B is the binding energy, mu is the gluon mass, and lambda is the parameter related to the quark gluon vertex. So those are our inputs, and with these inputs we can calculate some the valence probability, the part of the anti-aligned and aligned spins, and the F pi. So we did some analysis changing those parameters, and this red one reproduced the pion decay constant of experimental value. And now we fixed those parameters that I wrote here. And I will calculate all the other observables. I will use the same fixed parameter that I have now. In particular, we can see that in this model, we have the contribution beyond valence are important, are around 30%. So the valence probability here is 70%. Okay, so one thing that we can calculate is the pion electromagnetic form factor. And our calculation is this black curve, solid black curve. And the dashed black curve is the valence contribution. So we can see that first, we have a good agreement with experimental data. And second, for high energy, our valence contribution coincides with the full contributions that is expected. And in the right panel, I also plotted this asymptotic expression from Brody-Lepage. And we can see that for high energy, we can also recover the expression, which is essentially perturbative QCD. Okay, so this is the electromagnetic form factor. And we can calculate the pion charge radius. And this is the same parameter that I used before. And our pion charge radius is in agreement with the PDG values. It's in fair agreement. And we can also go on and calculate the transverse momentum distributions. So we learned in the first talk of yesterday how important are calculating this kind of distributions to understand the structure of the hadrons. And here I will calculate the twist 2 and twist 3 TMDs. So I have all these operators. We can connect to the Betz-Salpeter amplitudes, and we can use the Betz-Salpeter solution that we already obtained and calculate these twist 2 and twist 3 contributions. Okay, so using the F1, we can integrate in this transverse momentum. This gamma is this transverse momentum. XC is the Bjorken variable. Okay, so and we can obtain the PDF, the pattern distribution function. So this is our PDF at the model scale. So in black is our full calculation, and in green this is the valence contribution. And one important behavior is to see how it goes to C equal to 1, how this approach to 0 here. And we extracted this power in our model is 1.4. Okay, we also wanted to compare with some lattice calculation for low order Mealy moments. And these low order Mealy moments are calculated on 2 GeV and 5.2 GeV. So in order to compare with these lattice calculations, we have to evolve from the model scale to these two scales. So to do this, essentially we followed the work by Q in this EPJC, where he used lowest order de Gleb equations and the effective charge. So using this, the concept of effective charge, we set our scale. So our model scale is 360 MeV, and we performed evolutions. And these are our results using this prescription, and those are the last QCD for 2 GeV and for 5.2 GeVs. So we can see that we have a good agreement with lattice QCD. And those are from where we take these large QCD calculations. Okay, so we can also compare our calculations with data. So we know that there is this old experimental data from E615, that is this red points here. And those data was reanalyzed from Aisha in 2010 using the resummation effects. And this resummation data is plotted here. And the black curve is our calculation to this same scale, 5.2 GeV. And we can see that we can have a good agreement with this reanalyzed data from Aisha. And the green one is our valence contribution. And we can also compare with all the theoretical calculations. So here we plotted some of the theoretical calculations that we found. So we have two different Dine-Schwinger equation calculations. In green, we have the BURFQ collaborations. The gray area are large QCD results. So these gray area that are very here. And black and orange are vertical lines, GEN collaboration that it's not published, it's a private communication that they gave to us. And in this evolved result, we can also calculate our exponent, and now is 2.94 in our calculation. And those are the exponents for large QCD, 2.2, and the work by Kui et al. That use the Dine-Schwinger equation is 2.81. So it's so we know that there is a great debate between what would be the correct power here. So and here are our outcome. Okay, so here I'm showing the twist tree plots for in terms of the Bjorken variables, and I separate the full calculation and the antisymmetric and symmetric contribution. So and I define it in this way: it's antisymmetric and symmetric contributions. And this is the three-dimensional plots in terms of the transverse momentum and the longitudinal momentum. In terms of twist 2, we can see that we have a peak for Xi 1/2, and we have the vanishing values and the endpoints. And for gamma greater than 2, the order of magnitude falls off very, very fast. Comparing with all the theoretical calculations, we can say that our result is similar from Dine-Schwinger equation calculations, but different from light front constituent model and these light front holographic models from Baqueta. So there is a different behavior here. In particular, this for twist 2, they present some double humps here that we see in twist 3. So in twist 3, we have these double humps here. And these for large gamma, they disappear. Okay, so one other interesting thing that we can do is to take our pion and go to the configuration space. So we define a configuration space that is a Cartesian product of the eye of time and the plane expanded by the transverse coordinates. And this is the eye of time. This is the tilde. And we can perform this. and we can show this pion image, the three-dimensional pion image. This is in this configurational space. Okay, so all I presented was considering fixed mass quark and gluon. And one idea that we have that we know that it's important is to address the quark propagator. So, and we started to analyze this, how to perform this. And in particular, we started with Abigail, that she calculated using a phenomenological running mass that entered in the addressed quark propagator. So this is a phenomenological expression for the running mass. And we took the lattice QCD calculation from Orlando. That is the black curve here is the lattice QCD calculation. There is a fit of the lattice QCD calculation. And the blue one is a fitting for these three parameters, M0, M, and lambda for this mass function. So Abigail take this running mass and solved the Betzel-Peter equation for two fermions. So she used these dressed quark propagators and to calculate in Minkowski space, we also used integral representation for the vector and for the scalar part of the propagator. So this is the Callan-Lehmann representation. And in the end, we obtain a coupled system of integral equation, and we can solve it numerically. And then we have here longitudinal momentum distributions. So here I'm presenting a comparison between two different binding energies. This is big M is the mass of the bound states. So two different mass, two different binding energies, and comparing with this running mass model and fixed quark mass. So the dashed is the fixed quark, and the full is our running mass. So we can compare the longitudinal momentum distributions and the transverse momentum distributions. And we can see that inserting this running mass model, this transverse momentum leave more, so they can reach higher transverse momentum. Okay, this was done using this phenomenological model for this mass function. But what we intend to do is to really solve the Schwinger-Dazer equation. So we did it in collaboration with Diana Duarte. And we considered a simple model, which is a bare vertex, massive vector boson, and Pauli-Wheeler regulators. So we take this rainbow ladder Schwinger-Dazer equation in Minkowski space, and we solved this. So we also consider a massive gauge boson given by this expression here in covariant gauges. And the addressed frame propagator, we wrote in this way. And this function A and B, we use in Callan-Lehmann representation. So using this Callan-Lehmann representation is essential to deal in this Minkowski space program. So we can write this Dyson-Schwinger equation in this way, and we solve it numerically. And we calibrate the model to reproduce this mass function that we took from lattice data. Okay, so we can set the model parameters in order to have this dynamical chiral symmetry breaking. And of course, what our aim now is to use this solution that we found and calculate this the Betz-Salpeter equation. So we can have both a solution of the Dyson-Schwinger equation and the Betz-Salpeter equation. This is what we are pursuing now. Okay, so those are my conclusions, that the near future will offer an innovative view of the dynamics inside the hadrons. And we want to try to perform this 3D tomography of hadrons. And up to now, with using this simple model, we calculate electromagnetic form factor, PDF, TMDs. And we also presented this 3D imaging that is in line of the goal of the future electron-ion collider. And our future plan is to include the dressing function for quarks and gluons, and also a more realistic quark-gluon vertex. Thank you.
Thanks, Wayne, for the talk, and also respect the time. Please.
So I have just a couple of questions. First one was this PDF you mentioned about near balanced pion wave functions near X1 regions. And you were talking about this Acher and Fogelsang's resummation result with the comparison with yours, which looks...
This one?
Yeah.
Okay.
So this one, one has to, I mean, this kind of general comment.
Okay.
That this resummation uses a particular prescription for the resummations. There are several different ones. We have used a few different ones. So here they use a so-called, instead of double Mellin conversion, they use the so-called Fourier-Mellin conversion. And then there is some caveats with that. There are some approximations which neglect some of the terms and so on. So we actually mentioned that double Mellin is the way to go. And it shows actually very consistent with the red ones, not with the black ones.
Ah, okay. So you are saying
so
that
it's like
it could be this.
That's right.
Okay.
It's more like 1 minus x with the first power rather than square. So that's things one has to really look into. And then you mentioned the JAM work was in private communication, but it's actually published. You know.
Ah, okay. Yeah. But so I have to introduce it.
Yeah. So that was last year in PRM.
Okay.
Yeah, and then the thing that confuses me a little bit about this gluon mass again. You know, in the previous talk that the speaker was talking about the this Landau gauge and the this ghost coupling and so on. But in the if you are going to use the light front formulation, where we typically use the light front gauge, then there is no ghost in the light front QCD. So therefore, I'm a little bit puzzled about your gluon mass, as if it was like a previous talk and so on. That confuses me. And then also, I think it better be analyzed, what are the different results you get if your gluon mass going into very close to zero and so on. So that's something interesting to look at.
Okay. Okay, thank you.
Okay, more questions or comments? Tobias.
Just want to comment this point of the gluon mass. Indeed, in BLFQ, the gluon mass is very similar to the one we use. And they work directly as in the light front gauge. We work in Feynman gauge. But in terms of scale, is more or less the same mass. Okay, yeah. Just to remind that.
More comments? Yeah.
Hi, Wayne.
Hello.
Sorry, my very loud voice. So I was wondering, how do you treat the Wilson lines in your TMD definition? Because I see your calculations are performed in Feynman gauge, right? But when I don't understand how did you obtain your TMDs? But in general, if you go back to slide 12.
Okay. Okay.
There, back.
Yes.
You have a one that you're introducing a twist two, for instance. And in general, we need a Wilson line, right? Connecting your quark and anti-quark fields for gauging variance. So how do you deal with the Wilson lines?
We use here the Mandelstam framework, Mandelstam, and we can connect this with the Betz-Peter amplitudes. So,
okay.
So the Wilson line, we don't.
So you don't need to consider Wilson lines at all to obtain a TMD? Is that the case?
No, I think yes, it depends on the gauge choice, but
it is independent of the gauge choice? No, of course, because it's unobservable, but still you need to be consistent in your calculation, right?
Oh, yes.
I'm just, actually the question is just like, because I know in Dyson-Schwinger, we usually perform all calculations in Landau gauge, right? But at the same time, people also take the Wilson line to one as if they were in Light-Cone gauge.
Yes.
So there is some kind of inconsistency.
Yes.
So I just wanted to see.
Oh, yes,
Okay. Okay, good. Thank you.
Yeah.
Another question or comments? If not, okay, I can return at 4 p.m. to continue. Thank you. I don't know. Exato. Aí. Institute of Modern Physics, that's right? EMP. It's written like this. I don't know. I think you need to put on the appear like that's working. Okay. Okay, I can start the first talk after the coffee break with Shirat Najir from Institute of Modern Physics from China. He speak about the proton gravitational form factor with the basis light quantization. Please go ahead.
Yes, so today I will talk about the proton gravitational form factor within our basis light front quantization formalism. So before I begin, I would like to thank the organizers, and this is a collaborative effort from experts from different groups. So what is basis light front quantization? So this slide demonstrates a brief description of how we proceed to calculate observables using this formalism. So first of all, it is a non-perturbative approach. And yeah, so I was saying this is a non-perturbative approach and it is based on the Hamiltonian formalism. And we solve the light front eigenvalue equation. And the basic general algorithm to solve a system in this formalism is that you construct your Hamiltonian in the light front formalism and you select a basis state, and then you calculate the matrix element and you diagonalize this matrix element and calculate the observables. So let me start by showing you the effective Hamiltonian that we use for the valence Fock sector for the proton with 3 quarks. So as you can see, this has already been demonstrated, but I will just like to go through it again. So the first term, as you know, is the kinetic energy term. And we have this confining potential, both in the longitudinal as well as the transverse position. And also we have this one gluon interaction term. And for example, here, this kappa here represents the strength of this confining potential, and we have the same strength for both the transverse and the longitudinal confining potential. So in effect, this is a 3-dimensional confining potential. Okay, let's move on. So what basis do we choose for this approach? In the longitudinal direction, we have the plane wave basis, and in the transverse direction, we use the 2-dimensional harmonic oscillator basis. And since this is a numerical approach, we have to have some truncation. So for example, in the transverse direction, we have this truncation parameter Nmax. So we choose an Nmax such that it obeys this inequality. And in the longitudinal direction, we have this truncation parameter K. So not only that we truncate the Fock sector, but for each Fock sector, we have this 2 truncation parameter Kmax and Nmax. And in this way, we can construct our light front wave function using these basis states. And this is a representation of how we could write it. And here, this is the harmonic oscillator wave function. So now that I have shown you how we construct this wave function, now I want to show you how to calculate the gravitational form factor using this proton wave function for the valence Fock sector. So before that, to give you an idea of the gravitational form factor, they are connected with energy momentum tensor. So here I show you the energy momentum tensor, the gauge invariant energy momentum tensor in the symmetric case. As you see, as you can see, you have the fermionic part and the gauge bosonic part. So firstly, I will focus on the fermionic part, and this is the energy momentum tensor that I will be considering. So the idea is that the matrix element of these energy momentum tensor are connected to the gravitational form factors. via this kind of parameterization. So here you see the parameterization of the energy momentum tensor. And for a spin half system with a symmetric energy momentum tensor, you will have 4 gravitational form factors, which are usually represented by the alphabets A, B, C, and C bar. And in particular, this C bar form factor is important in the sense that it's related to the pressure and basically the mechanical forces inside the proton. And how do we extract these form factors? For instance, the A and B form factor, they can be extracted from the plus component of the energy momentum tensor. And the remaining 2 form factors, C and C bar, they can be extracted from the transverse components, the IJ components 1 and 2. So we calculate all these 4 gravitational form factors for the leading Fock sector in the proton. And now I will show you the results for these gravitational form factors. So firstly, I will show you the results for the form factor A and B. So on the left panel, you see A, and on the right, you have B. So note that you have 2 central lines. So the magenta line is our work at an initial scale. And we want to compare it with the available lattice data. So we do an evolution using, we do an DigiLab evolution from our initial scale to the scale at which the data is, which is 4 GeV square. And the blue band with this dot dashed line, that is the evolved result. And same here for the form factor B. One thing to note is that at the initial scale, which is the magenta line, they both A and B obey the sum rule, which is basically related to the fact that the conservation of momentum and angular momentum. So once we have evolved this, we can see the comparison with the lattice data. Here we observe that in our case, our result after evolution is slightly below the lattice data. And at the 0 point, here our results are slightly again below the lattice data. Now we look at the D form factor. Now this D term is actually related to the C form factor by a factor of 4. So D is actually 4 times C. And this D form factor came into light after we have this pressure distribution, after the pressure distribution inside the proton was measured for the first time. And this gave a tremendous boost to looking for this D form factor in various formalisms. And for example, the most important aspect of this D form factor is that the value of the D form factor at Q square 0 is not constrained by any conservation law, unlike, for example, the A and B form factor. So only you can experimentally find out what the value actually is. So it's very important to find out the value of D at Q square equal to 0. And again, as I said before, it's also related to the pressure and basically the mechanical properties inside this proton. So let me show you the results for our D form factor as well as the C bar form factor. So on the left, you see the D form factor. Here we show comparisons with a lot of phenomenological and experimental data that were available. Again I say that the blue line is our results after evolution. The magenta is the work at the initial scale. Again, we want to compare it with data at 4 GeV square. Now you can see that after evolution, it is quite consistent with the JLab data, as well as with other phenomenological models. And the key point here is to note that D is negative. A negative D implies that you have a system which has stability inside it. And on the right panel, I show you the results for the C bar form factor. Again, I compare it with the bag model and the multipole model, and it seems to be consistent. And again, C bar is also found to be negative. Let's move on. We also do a fit for our form factors. This fit is important in the sense to have a closed expression for our form factors in order to do some Fourier transform or further calculations. So for example, we choose this multifold form for our form factors. And here I just show you the fit for the D form factor, but we have done this similar fit for all the form factors. And for example, here I show you in the bottom table the parameters for this A0, A1, and A2 for this two fits. And you can see that it fits quite well. Now, once we have this D form factor, you can also calculate the pressure and the energy density as well as the mechanical square radius, which are related to the D form factor. Also, this energy density is related to the A as well as the D form factor. So in this table, for example, the first line is our results for all these three observables, and I compare it with the available results. As you can see, our pressure E0 is slightly less than this QCDSR results. And our energy density is again slightly on the lesser side. But our mechanical radius is slightly larger as compared to the available two results. Now, we can do a Fourier transform of this D form factor and calculate the pressure and shear in the impact parameter space. So for example, you have this pressure and shear distribution written in terms of this Fourier transform. Here B represents the impact parameter. And once you have the pressure and shear distribution, you can take a linear combination of them, and they are related to the normal and tangential force. This one. So now we are in a position to calculate all of these four, the pressure, shear, and these two normal and tangential forces. And these are the results for the pressure and shear distribution. So on the left, there is pressure, on the right, there is shear. So one important criteria for the pressure distribution is that, I mean, the criteria for the stability of the system is that it should obey this condition, which implies that there must at least be this one node or a crossing at zero crossing, which we observe in our case. And again, we compare it with the Light-Cone sum rule results and again the fitting obtained from the JLab data. And as usual, we have both the results at the initial scale as well as the results at the evolved scale. And here's interestingly, we find that our result after evolution is slightly less. Slightly less than the results with the Light-Cone sum rule and the JLab results. In fact, our initial scale results are more closer to those results. And similar observation can be found for the shear distribution as well. And the shear distribution, you can see that it's a positive quantity, which is a typical thing observed in hydrodynamic system. And again, we have compared our shear distribution with these two results. Now we show the results for the forces. So on the left, we have the normal force and the tangential force. Again, note that these two forces, they are a linear combination of the pressure and the shear distribution. And for example, here we see that the normal force is positive, but the tangential force has both positive as well as negative regions, which indicates that there are regions inside the proton where it is repulsive as well as attractive, which is required for a stable system. And you can see that the magnitude of this repulsive, this is the magnitude of the repulsive and the attractive forces. And this magnitude is larger than this magnitude, which ensures that the system overall is stable. Now we also calculate something called as the two-dimensional Galilean distributions. These are again related to all these form factors that were calculated. The form factor in the impact parameter space. And this is just the definition of them in terms of the form factors. And for instance, this mu here is the energy density. Again, the radial pressure, the tangential pressure, this is the isotropic pressure, and this is the pressure anisotropy. So I show these equations because I will be showing you the results for those. For example, here, this is the result for the energy density mu. Again, we compare it with a multipole model shown in this paper. And we see that overall there is a consistent behavior with this multipole model. And interestingly, here in this case, we observe that after evolution. We observe that after evolution, our results are much more consistent with the multipole model. Again, this is the result for the radial and tangential pressure. And again, as you can see, the radial pressure has a positive nature and the tangential pressure has both positive and negative region. And again, they are consistent with the multipole model after we do the evolution at this scale. And finally, we have the pressure anisotropy here and the radial pressure. And it should be noted that these two sigma and the capital pi, they are a linear combination of the radial and tangential pressure. So this is expected result because our radial pressure was positive. So we can find that the pressure anisotropy is also positive here, which implies that sigma r is greater than sigma t. Okay, now we add a dynamical gluon to our valence Fock sector, and we want to study what is the effect of the gluon in all this. So again, this slide has been shown before, but let me just quickly go through it. So here we have added this QCD interaction. This was previously the transverse confining potential and the longitudinal confining potential, which is there in the first Fock sector. And here for the second Fock sector, the interaction, we have these two interactions. So this is the vertex interaction and the instantaneous one gluon exchange interaction. And here I show you what are the parameters that were used for this calculation with the one dynamical gluon. For example, the transverse and the longitudinal truncation parameters were set at these two values. And these are just all the parameters that were involved. And just to highlight the fact that these parameters are set such that all the properties will be satisfied. Okay, now this is the result for the A and the B form factor with a dynamical gluon. This is at the initial scale. Again, you can see that A and B must obey, or it should obey this sum rule, which is that after you add all of the contributions from UD and the gluon, you should get 1, which is the conservation of momentum. And here you see this vanishing of the anomalous gravitomagnetic moment, which is the fact that when you add all of them, it should be 0. And in the table here, I show you the values for each flavor. For example, this is the form factor A for the U quark, and so on and so forth. And here this is the total. And since this is a numerical calculation, I show you the exact value that we get. Now we evolve, the previous slide was the result at the initial scale. Now we evolve the results to a final scale. Again, we see that, okay, this magenta line is the result for the total quark. That is the quark from both the first and the second Fock sector. And this blue dotted line is the result for the gluon. Again, we observe that our results when compared to lattice is slightly lower, but within error bar for at least for the quarks. And similarly for the B form factor. And here I show you the results, the value at Q square equal to 0 for all the flavor and also for the gluon. So these were the results for the A and B form factor for the gluon. Now this is the result for the D form factor with one dynamical gluon. For example, I here compare our results with the available lattice results. This is a previous result and these are the recent lattice results. And again, we do the evolution. So for example, the dotted are the results at initial scale and the dot dashed are the results after evolution. So you can see that they are much more consistent, or they approach the lattice results after evolution. And again, to emphasize the fact that the D form factor has to be negative to imply a stable system. And we observe that the gluon D form factor is also negative. So again, we calculate the same mechanical properties for this with this dynamical gluon. So for example, these are our results for the quark and for the gluon after we do an evolution from this initial scale. And we observe these values for the pressure, energy, and the mechanical radius squared. And we again show you the preliminary results for the pressure and shear distribution, now with one dynamical gluon. So on the left, we have on the left top, we have the pressure distribution, and the left, right, we have the pressure distribution for the gluon. So this is for the quark case, and this is for the gluon. So here I again compare with the available results for the quark, and the blue line is after evolution. So to see here is that they again have they obey this condition that you have this node, and so this ensures there is this stability, and the shear distribution is a positive definite quantity, as you can see, for both the quark and gluon. So that is all that I have to say. So I will conclude by saying that we calculated the gravitational form factor for the proton in the valence Fock sector, as well as by adding a dynamical gluon, and we found consistent results with the lattice data, and also the D term was found to be negative and consistent with lattice data. And we are in progress of calculating the C-bar form factor for the gluon, which is a key to this sum rule, which says that the total C-bar has to be 0 at all Q square values. So that's it, and I will leave by showing you the upcoming talks from our team. There are a lot of talks, and I hope you will attend all of them. Thank you.
Thank you for the nice talk, and open to questions or comments, please. Yeah, so sure.
So I'm a little bit puzzled by comparison with the quark sector with the JLab data, because as I understand that in experiment, right, they don't care whether it's a quark contribution or gluon contribution, right? It's a whole thing. So why you're comparing only the quark sector with the JLab, not adding both of them?
You mean this comparison?
Experimental data. Experimental data, of course, is both quarks and gluon contribution altogether, right? The experimental data doesn't care.
But this data is for U plus D, the quark flavor U plus D, and they have
they separate
they have shown it
from the experiment.
They have shown it separately.
So they have also the gluon.
Yes, they have. Yes.
So they separate.
Yes,
just like lattice data they do.
This is lattice.
Yeah, but the JLab is I'm confused. So the JLab lattice data, not the experimental data.
You mean this? Wait, let me go back.
I mean, I was confusing that.
You mean
this? JLab, when you mentioned JLab data, I thought that it was experimental data.
This is from the experimental data. This is for
so the experimental data don't care whether it's a quark or gluon contribution. It's all together, right?
Yes, exactly.
But that's a theory, but the experimental data don't care, right? Okay, so this was based on that assumption.
Yes, this was based on that assumption, right?
You like made question? No? Yeah. Okay, another question, Leticia. Just 1 second, please.
So thank you for your talk. I have kind of a naive question, I guess. So in your confinement modeling in the beginning, your Hamiltonian, right? This is just quark confinement, right? That you're implementing with this potential.
Yes.
I see. So in principle, the gluons are not confined in your
for
model.
the valence Fock sector, we have this interaction term.
One gluon exchange is just okay. You don't have to, because I was wondering for the pressure part. In the end, whenever you have a negative contribution, like when you go
for the pressure distribution of the gluon.
Yes, like this one, for example, when you go to the negative, you have a negative contribution around 1 Fermi. Yes. Usually, people refer to this as like a signal that it's like a confining force, right? And like confining pressure, because you have. And why would you have this type of negative contribution also for the gluons if they are not confined in your model? That's my question. So in the end, you show the plot for the gluon contribution to the pressure, and you also see this negative part, right?
Right. So this behavior comes from the fact that the D term is negative. if you have a D term which is negative, then you will always observe this kind of pattern. And we found that the D term is negative for the gluon as well. So that's why if you look at the plot, the pressure distribution for the gluon, yes. Right. But, right. Right. I mean, I'm saying that the fact that you see this behavior is a fact is because of the D term being negative. Right. Physically, let's see. Yeah, so this is our Hamiltonian with the one dynamical gluon. So we have confining potential in the first Fock sector, but we don't have any confining potential for the gluon. We have this QCD interaction. Right. Right. There is a non-zero gluon mass.
Okay, Fernando.
Can you show the plot of the normal force as a function of the impact parameter, or B? Or... Right. No, it's F.
Yes.
That one. Why isn't it sometimes negative?
Which one?
The first one, Fn as a function of B. Shouldn't it be negative sometimes? It's always positive all the way?
Yeah, it looks like it's always positive all the way. Why do you say it has to be negative at certain regions?
Because you see some,
it is,
as people were mentioning, Leticia were mentioning, you may have sometimes attraction in some region there. You have attraction, which is the negative pressure, and this is compatible with sometimes a negative force, isn't it? Or I didn't understand the thing.
Right. It depends on the linear combination of the pressure and the shear. So based on the magnitude of the pressure and shear, in that particular B range, it's not going negative.
So then you expect that you have some repulsion in the system because of that. If the force is positive,
it's
normal,
it's always
pointing outwards.
Yes.
So it's
but the stability is determined by the tangential force also, right? It has the negative region and the positive tangential force as well, right? I mean, it should be an interplay between both the normal and the tangential to have the complete stability. So I would say that is why we have this region also in this.
Okay, more questions or comments? Very short if you want. Okay, thanks again to Nair. And the next talk, please. It is, I don't know. Jiangsan.
Yes.
Lan from the China also speak about beyond valence distribution hadron with the basis like quantization. Please go ahead.
Thank you. I'm Jiangsan Lan from IMP, and my boss is Xingbo Zhao, and we work with Professor James Very and Tobias and our students and postdoc. I'm very happy to come here. This is my first time to in person attend the Light-Cone, and 3 months ago, Professor Very and Kamelov visited us, and today I come here, and I'm very happy to meet you. And okay, next is my outline. I will briefly introduce our approach BRFQ, and introduce our some work. And this one is the new results. We work with Tobias, and we will also show some recent results. Okay, basically, we are calculate eigenvalue problems, just like Professor Very introduced yesterday. And here, okay, I want to mention the Shi will give a talk for the baryon tomorrow. And today I will introduce something results for the mesons. We use the Fox sectors to QQ bar and the Q bar G here. And our transverse, we use the harmonical oscillate basis, and longitudinal we use plane wave. And here we truncate with MS and KMS, they related to the UV cutoff and the IR cutoff. This is the first work we use the NJL in effective Hamiltonian interactions, and we consider the meson is QQ bar systems, and we have connected part and confinement, and we diagnose our effective Hamiltonian and got the wave function. Then we can got the initial pattern distribution function, and then we use the QCD evolution. We can got the high scales PDF, and this is for the pion PDF, and this is for the kaon. We calculate the ratios for the up quark, and we find our result is not so bad. And next we got the moment of the pion and the kaon. Here I show the result for the pion. We can got that here is the first moment and the second moment, third moment, and the fourth moment. We can got that the first moment is depend with the mu scale, it will decrease, and then we can use the first moment to fit the initial scale. And here we also find a 4GUA square, our pion, the valence gluon and the C is close to the BSE's results. And here we can compare with others, lattice and James results. Okay, and this one is the Joyan concessions. Here, this is the hard part, and here we use the pion PDF and the nucleon PDF, and we can roughly got the results compared with the data. And next, we replace the effective NJL interaction, use the quark gluon interactions here, and we consider one dynamic gluon, and we also have confinement now, and here the quark gluon vortex can read from the LIFO QCD Hamiltonians, and then when we solve the problems, we got the eigenvalue and the eigenvector. We can here we use the blue, the six blue states to fit our parameters, six parameters, and we can find that the first Fox setters for pion allowed 50%, and the second Fox setters allowed 50%. And here we got the pi 1 is dominated by second Fox setters, and here the decay constant of the pi is smaller than this pi. Okay, and next we can got the wave function we showed in leading Fox setters, because this two-body wave function we can easily to show. And here is the quark. we can got their nano when x small and large. Okay. Next, we use the V function. We can calculate the EM form factors, and we wrap. This result is our output, not a fitting results. We can roughly agree with the data, and the large behavior is allowed q square. Again, we can calculate the PDA, use the Life-on V functions, and we follow this paper to evolve the initial PDA to 10 GeV squares. We got our result is close to the perturbative QCD's result, and agreeing with the data. Okay. And again, we use our V function. We can calculate the PDF in model scale. We find that compare with the NGL's results, where we consider pi is a QQ bar. Now the valence PDF no symmetry now, and here if we only consider the first Fock sectors, we can already got the symmetries with the x equal half. And now we can have a look at the valence PDF in the model scale have enhanced small x range, and then this valence PDF is interesting. Look like the logo. Maybe tubules have some. And this is enhanced in small x range, and this is the peak, and here is the large x when x close to 1, the behavior. And here we compare with the BLFQ and JLO, we got the initial scale is increased, and here we have 21% contribution for the moment from gluon. Okay, and when we evolve to the 16 GeV square, and we can roughly describe the data, and we got our gluon distribution is enhanced compared with BLFQ and JLO results, and this is agree with BSE's results. And here we use the J-PARC productions concession, because these concessions, the gluon contribution is large. We can use this one to evaluate our PDF pion PDF. And this is the hard part. And again, this is pion PDF, and this is taken from nuclear NC text. And we can roughly agree with few different targets and with different energy beams results. And interesting is we work with Tobias and Emmanuel because we know now BSE can describe the pion and the kaon and the protons, the Life-on V functions, and they got a lot of results. And we use the BLFQ and the BSE. We take them together and compare. Okay. Basically, we know we can write the Hamiltonian here, and we can write the V functions like QQ bar and the QQ bar G and more QQ bar GG others. And if we take pion is Q bar plus Q bar G, then we can write the Q bar G Fock sectors wave functions can be used Q bar and with the interactions connected to the Q bar and the Q bar G sectors. And here we can follow the Brusky's papers. We can take here is the spin flip matrix elements, and we find here MF is the quark mass when we consider the quark gluon vortex interactions. And now we can read our PDF contribution from second Fock sectors. And here, if we choose a simple power law form for the wave functions, then we can fit with the BSE and the BLFQs to got here have two parameters here. And then now we got the perturbative QCD's pion wave functions. And we can use the QQ bar Fock sectors wave function to got the Q bar G wave function and got the PDF contribution from the second Fock sectors. And here we compare our results with BSE and the perturbative results when we consider the quark mass and gluon mass taken from BLFQ and BSE. And here we can got some results that the model 2 is we take the quark mass and gluon mass from BLFQ, and we find the perturbative QCD's results have a peak here, a smallest range. And when we can compare the model 1 and the model 2, model 1 is that we set the MF equal MQ, and we find that the enhance the MF will carry out a peak here. And when we compare BSE's results with the model 3 is take the parameter from the BSE, and we find here have some difference because here the BSE consider the infinite gluons. But however, we can got from this figure when we consider second Fock sectors, a small S range will carry a peak. And again, we consider we compare the gluon mass when we studied how gluon mass change will carry some difference. And we find that when we increase gluon mass, the quark contribution from second Fock sectors will go to small x range, the shift to small x. And for the gluon PDF, when we increase the gluon mass, the peak will shift to large x range. And the blue results compared with BLFQs is really simply agreeing with together. And finally, we got an enhancement of small x low a peak a small x range, and they will connect to the large spin split matrix elements, and that will carried the pi, a large pi low mass splitting. We got the result here. When MF decrease, the pi and the pi low mass split will decrease. And this one was proposed 25 years ago by professor. This professor, he said the enhanced spin flip will carry a large effect pi low mass splitting. And thus days, our postdoc Satvia Kur will calculate the low methods. He will introduce interesting results Tuesdays. And our Kai Yufu, he tried use the wave function to calculate the pion TMD. And yes, for the papers, we can use our wave function to calculate some results for the TMD. We got the quark and the gluon. The K-purple is around the point test GV. And here again for the GPD, here we can also got the result enhanced a small S range. And we can also got the gluon GPD. And our PhD students, Ziqi Zhang, he calculated the general skewness GPDs. And this one, we also found a peak, a large probability a small S range. He will here. And our PhD students, Jialin Chen, we try to use our systems to consider SS bar and the SS bar G. And next we calculate the K-on systems. And here, because they are line methods, so we consider other parameters is the same and just tune the S quark mass, the mass of S quark and the phenomenon called MF for the S quark. And we use these two states to fit these parameters. And then we directly got the K-on and the K star. Okay, almost finished. And interesting we can got the K-on decay constants is close to the PDG's value. And here again, we can show the K-on wave function. And we use the K-on wave function, we can also calculate the K-on EM form factors. The result is not so bad. Again, the PDA, the behavior is close to particular QCD. And again, we can have a look. The valence PDF is look like the logo. And here we can got the value light quark and S quark. The moment is in initial scale is around 4 to 5. And when we evolve to high scale, we can roughly got the results compared with the NA3. And here is a 20 GV squares, the pion and the K-on PDF from our model. And yes, some will have pion bin and the K-on bin, and he will measure some results, and we try to calculate the Joyan coefficient because the K-on is U S bar. They will K plus and K minus with the same targets, they will have huge difference, and we give some results. Maybe in future can have a check. Again, we can calculate the K-on's GPT. And here I want to mention is our PhD students, Zimin Zhu. They calculate the high twist PDF for the pion. They published in the early of this year. And now he also calculated the K-on's high twist TMD. And we can find that our result is we can follow some rules. We got the blue results just like symmetry with half and x equal yes, the integrate is 0. And I want to mention that G mentions that the mass can write by quark gluon and this one, and he said the A is contributions from the leading twist results, and the B is contribution by high twist results. And here we have EIC and the EICC in futures. And for EIC, we have high energy, and the EICC is low energy. And for low energies, the high twist will give more contributions. And anyway, in futures, when we have EIC, and we should study the high twist structure in futures. Finally, is the results. We can use our model to got mass spectrums and hadrons structure, and we got some results, and we can got a pilo mass splitting, and with a large spin flip matrix elements, and this will carry a peak and low F for the quark PDF. And we can calculate the gluon GPT TMD, and the Lamison can also to calculate the SS bar systems and the K-on systems. And in futures, our PhD student Jiatong will calculate the meson with more higher Fock sectors. Okay, welcome to visit us. This is our new campus in Guangdong, Huizhou, and this is the in future the EICC will be building here. Thank you.
Thanks for nice talk. Questions or comments, please?
Just a comment. Jean-Jean, put the transparency where you have the higher Fock component with the glue with 1 over the mass m square pi minus m naught. Just put that. I want to make a comment. Put the transparency.
Okay,
please. Yeah, because this is to clarify.
This one?
No, the one you computed.
This one?
No, the one, a formula. Go back. Just to explain. No, I want the formula.
Formula, okay.
Yes, the formula. Let me see. No, yes, this one. Below the blue arrow, you see how you compute the gluon, the QQ bar gluon for component. You have 1 over m square pi minus m naught square QQ gluon, and then times the potential and the confined part of the wave function for QQ bar. So because you have heavy masses, you never touch the continuum. So this is a bound wave function for the QQ bar gluon. This may explain, I mean, this also probably is the same when you compute the nucleus with 3 quarks and a gluon. And then you have indeed a bound system, even in this component. And this may help in interpreting the model and some of the results that we saw before even, and your calculations as well. Okay?
Okay, thank you.
Okay, more comments or question? If not, I have one. I think the slide 10, you have some parameters, no? I curious why you fix the parameters of the base light front. You have parameters, that's right?
Yes.
Yeah, why you fix?
Okay.
Or just
okay, let me go to this one. The quark
no, 10,
yeah.
10. Okay, it's the same way.
Yes.
Go ahead.
Any more?
More questions or no? Thanks again.
Thank you.
Now the last talk by you see how quantum stress and the light front.
Hello. Okay. First, I want to express my gratitude to the organizer for giving me the opportunity for sharing our work here. The talk today is based on this paper, which is completed in cooperation with Professor Yang Lin and Professor James Wary. Well, for a hadron which is governed by strong interaction, become probably structured by the other 3 fundamental forces. The 3 fundamental forces are coupled with hadron by the 3 currents. The hadrometric elements of the currents can be parameterized by gravitational by form factors. Take the nuclear energy momentum tensor as an example. It has 3 form factors. We call them gravitational form factors. In the forward limit, these form factors can give some global properties of hadron, like the hadron mass and the hadron spin. But before we know the detail of interaction, we have no idea about the exact value of D term, which is as fundamental as the hadron mass and hadron spin. This is the reason why the D term is often referred to as the last global unknown. According to the Lorentz decomposition, we know that the D term is related with the special components of energy momentum tensor. In coordinate space, it can be decomposed into the shear parts and the pressure parts. With this relation and the stability conditions of hadron, we can give some constraints for the D term. The first condition is the famous one-law condition. This condition means that the total pressure of hadron must vanish. With this condition, we expect that there is at least one node in the pressure. But this is a necessary condition for stability, is not sufficient. A stronger local stability condition is that the normal force in the hadron must be directed outside. And this condition can give a direct constraint for the D term, that the D term is negative. And this result has been proved by many model calculations. The coupling between graviton and hadron are weak. It's hard to detect the gravitational form factors directly. But fortunately, we have several indirect methods to assess its form factors, like the deeply virtual compton scattering and the double photon production process. The key of this indirective math is the J sum rule, which gives a relation between the generalized pattern distribution and the gravitational form factors. With these formalisms, it's convenient to assess the individual components of gluons and partons. Gluons and quarks, sorry. We have many formalisms help us to understand the gravitational form factors like the lattice QCD and the perturbative QCD, which can give the asymptotic behaviors of these gravitational form factors. The phenomenological models can give us a direct understanding of physics, like the Beck model and the Carroll-Clark-Soliton model can illustrate how the interaction generates the fermion D term. Well, the hadron is a non-perturbative system. Besides this amazing formalisms, the light from quantization is a natural framework to understand the hadron physics. The light from wave function representation provides a clear physical interpretation. With this representation, we can prove the anomalous gravito-magnetic moments is zero. And there are also many phenomenological models that use light from quantization, like the light from constituted quark model and the DSQCD models. The common difficulties of these models, of these formalisms, is to calculate the D form factors. These form factors contains interaction. Use the language of light from quantization. It contains the contribution of non-diagonal Fock sector, non-diagonal Fock sectors, which is proper renormalization. Okay, to obtain a proper renormalized gravitational form factors, here we consider a simple but non-trivial model, the scalar Yukawa model. All particles in these models are scalar particles and they couple through Yukawa type interaction. The Lagrangian of this model can be used to mimic the interaction between nucleon and pion. The original vacuum of phi-3 theory is unstable. So to avoid these problems and further simplify our calculation, we adopt crunched approximation, namely the contribution of nucleon and anti-nucleon loops is ignored. And under this approximation, only the nuclear mass needs to be renormalized. And in this theory, we consider the physical nuclear state, which can be expanded in the first space as one nucleon plus n dressed pion state. And this model has been solved up to 4 body sector truncations at a non-perturbative coupling. And the Bayer parameters like G0 and delta m squared are renormalized using Fock sector dependent renormalization. And according to the the renormalization parameters and observables like electromagnetic form factors, the Fock sector expansion was observed to achieve converge up to 3 body truncation. The energy momentum tensors in this theory can be represented by these diagrams. The different vortex represents the different contributions of the energy momentum tensor. The sector-dependent counterterms are named after different Fock sectors here. These diagrams can be calculated using the light front graphic rules, and with the light front wave functions, this formalism can be extended to non-perturbative regime. Some diagram contain interaction is divergence, like the diagram B and the diagram F. However, this divergence can cancel with exactly with the counterterms. The sector-dependent counterterm can be derived when solve the model. We can take 2 simple diagram A and diagram B as an example. The diagram B is divergence and it's exactly cancel with the counterpart in diagram A. Another important finding in this simple example in that the non-diagonal diagram A plus the diagonal diagram B produce a diagonal result. This is the fundamental of the light front wave function representations we derived later. Well, in light front dynamics, because we have to adopt approximation like Fock sector truncations, the four Lorentz symmetry is broken. We have more form factors than the Euro case. Well, in covariant light front dynamics, we can construct these form factors by introducing a null vector to indicate the direction of light cone. Well, in our model, we have two additional form factors, S1 and S2. Well, the plus and the plus minus components of the hydrometric elements are free of these two spurious form factors. So a combination of these two components are used to extract the form factor A, the gravitational form factors. Another popular choice to extract form factor D, the trace of the special components is invalid in our case because it contains spurious form factors. The form factors in the forward limit can be derived by the conservation laws. The plus mu components of energy momentum tensor is related with the four momentum operator. With the help of light from Schrödinger equation, we can derive an exact value of the T plus mu components of hydrometric elements. And in the forward limit, this relation is connected to the energy momentum conservation. The plus I components is related with the momentum conservation, and these two relations gives that A0 is equal to 1, and the P plus components is related with the energy conservation, and this can give a constraint about the form factor D. And this condition is exact what the one law condition is. And indeed, the D is finite in our model. Here we show some numerical results about the form factors. We calculate the form factors from a perturbative regime to the non-perturbative regime. And we can observe that in the perturbative regime, the behavior of form factors is close to the free case. And as the interaction increase, for example, the form factor D, it becomes more negative. And in the forward limit, A0 is equal to 1, which agrees with our expectation. And for large Q squared, these two form factors converge to the one body form factor contribution, which revealing that we have a point-like curve in our these systems. With the data of form factors, we can calculate the light front distribution like the matter density and pressure. Here to avoid the numerical difficulties, we use the fitting function. The light front distribution is just defined as the Fourier transformation of these form factors. And for the pressure form factor, we found a delta function as the original point, which means we have a hard repulsive curve at the center of the nucleus. The expecting node is located in the original point. According to our previous calculation, we can Yeah, thank you. Hello? Yeah. Well, based on previous calculation, we can summary light front wave function representations for T++ and T plus minus. And they are just a numerical density form. The light front wave function for T++, which had been derived by Borsky in 2000. The summation over G means that we pick up all the momentum of the momentum of each pattern. And in this work, we found a new light front representation for T plus minus. It has two parts. The first line is the kinematic parts, and the second line is the potential parts. Like the T plus plus, the kinematic parts mean that we pick up all kinematic energies of each pattern, and because here we adopt a quantity approximation, the interaction only acts on the nucleus. So there is no summation for the potential part, and if you observe this green potential part is just the Light-Cone energy minus the kinematic energy. And with these two light front representation, we can have a representation for D term. It's just the P plus times the energy. Of course, we need to subtract the contribution of A. And with this representation, we can easily find that the D term is finite, and if there is no interaction, it gives a free boson result. Okay, here is a summary. The form factor D of hadrons is remembered to be the last global unknown, and future works need to be done to involve the more physics to understand its nature. And in this work, we calculate the gravitational form factors of a strongly coupled scalar model and calculate its matter distribution and the pressure. We obtain a non-perturbative light front wave function representation for the D term, and these representations can be adopted in other phenomenological models by just replace the original interaction part as an effective interaction, and the capital R here means where the interactions at some. Okay, thank you. This is the end of my talk.
Thanks. Very nice talk. Now, question, comments, please. Um segundo, Edson, please. Microphone, please.
Okay, thank you. Nice talk, Carl. Please, which one is your 28 reference?
Sorry?
Reference number 28.
Number 20.
Which gives the GA value?
GA.
Yes, axial constant.
There are no this term, I think.
I think that it's in the second slide, second transparency.
Which page?
02, number 2. Just for curiosity, there's no implicit question. Number 2, please.
Yeah. No, this?
Yes, GA 1.26. Which one is 28? 28 is a reference?
Oh, it's actually the table is picked up from Polyakov well, and I think this is the uncertainty. What?
No, it's the error bar.
Yeah, it's an error.
GA, no? The error bar. Another, I don't know, comments or questions.
Maybe it's a little confusing.
Yeah, no. No questions or comments? Okay, I can thanks again. Thank you. Tobias, have somebody with that.
Again, please, the morning speakers, don't forget to send today your presentations, no? But to the Light-Cone email and to Rogério at CBPF, okay? And if you are able, also please upload in the Indico page. I know that Indico page is not working well, but if you are able, please do so. But send to the two emails your presentation, okay, for tomorrow morning. Thank you. So enjoy the rest of the day. Ciao.